Welcome to the Deep Dive, the show where we take complex, cutting-edge research, and I mean really cutting edge, and we take it apart, piece by piece.
That's the goal, to give you that fundamental understanding, that deep knowledge, but without all the jargon you'd normally have to wade through.
And today, we are embarking on, well, a pretty monumental task. We're stepping into the world of algebraic geometry and topology, extremely advanced stuff.
We're going to analyze a paper whose core finding is not only, mathematically beautiful, but the way it was discovered. It marks a really profound shift in how pure mathematics is being done.
That's right. So if you're listening, just know we are not aiming for speed here at all. We are aiming for comprehension. Our deep dive today is into a paper titled "The MOTIVIC Class of the Space of Genus 0 Maps to the Flag Variety."
And our mission is to trace the complete, rigorous, multi-step proof that holds up the main theorem. And, just as importantly, to understand the absolutely revolutionary role that advanced AI models played in its creation.
It's a paper that asks this huge question: what is the fundamental geometric nature of a space of algebraic functions?
And it provides a startlingly simple answer.
Yeah.
So I think we have to start with the title itself. Every single word here is essential to the argument.
Okay, let's do it. That covers our introduction. We have our paper. We have our mission. I think we're ready to jump in.
Absolutely. Let's start at the very beginning.
Title and authors.
Okay, so this monumental title. Let's unpack it, and let's start with the heart of the classification system they're using, the MOTIVIC class. If I'm listening to this, what on earth does MOTIVIC even mean? Why not something simpler, like, dimension or shape?
That's the perfect question. MOTIVIC class is a very technical term. It refers to the class of a variety, and by variety we mean a geometric object defined by polynomial equations inside a very specific algebraic structure. It's called the Grothendieck group of varieties.
The Grothendieck group, right? That sounds like the first big concept we need to pin down. It's the bedrock of this whole paper. But for most of us, it sounds, well, impossibly abstract.
It does, but the core idea is surprisingly intuitive. You can think of the Grothendieck group as a system designed to classify these complex geometric objects, these varieties, not by their exact shape, but based on a looser kind of equivalence. You could call it cut and paste equivalent.
Cut and paste equivalent. So if I have a really complicated shape, a variety, but I can show that I can, say, cut it up into a few distinct pieces, and then I can reassemble those exact same pieces to form a much simpler, well-understood variety, then in this Grothendieck group, they're considered the same. They have the same MOTIVIC class.
Exactly. They have the same Lego brick composition, you could say. The formal rule that makes this all work, the one that justifies every step in the proof we're about to see, is called excision.
Okay.
If you have a variety X and inside it there's a closed subvariety Y, then the class of X, which we write as X, is just the sum of the class of Y, Y, and the class of what's left over, the class of X without Y, X, Y.
So it's literally just saying the whole is the sum of its parts. This algebraic license to just break down and recombine these incredibly complex spaces, that's the key that unlocks the entire proof.
It is. Now, within this Grothendieck group, there's one very special element that acts as a kind of unit of measure. It's often written as a blackboard bold L.
And what does that L represent?
That L, or L, represents the class of the affine line, latex, math BBA1K, phonetic, the class of A1K. The affine line is just, a one-dimensional space. It's the simplest, non-trivial variety. So this class L acts like a variable in a polynomial. And this is really important because later on, when the paper discusses counting points over a finite field, say FQ, the value of L just becomes the number Q. This framework lets the proof work over any field, not just, say, the complex numbers.
Wow, okay. So we've covered the title, specifically the term MOTIVIC class and the Grothendieck group. Have we missed any initial nuances there?
I think we've established the high-level concepts. We have our tool, this cut-and-paste classification system from the Grothendieck group. We're ready for the next part of the title.
Okay, that solidifies the tool. Now let's move to the object that's actually being classified here, the space of genus 0 maps.
Right. So this defines the functions that the paper is studying. Genus 0 maps are specifically algebraic maps that come from the projective line, latex, math BP1, phonetic, P1.
And topologically, P1 is just the Riemann sphere, right? A surface with no holes, which is why it's called genus 0.
Exactly. And the space of maps is the variety itself. It's what's called a moduli space. It's a geometric object where every single point represents an entire function.
So just to be clear for everyone listening, the object we're trying to classify isn't a simple shape. It's a highly nonlinear, incredibly complex space where each point is a map.
Precisely. And finally, the last part of the title, where are these maps going? To the flag variety.
What is this object? It's described as fundamental.
It really is. It's a foundational object in algebraic geometry, and it's defined by chains of nested subspaces inside a bigger vector space. For now, you can just think of it as a very specialized, highly structured space that organizes all the possible ways you can choose these sequences of nested linear subspaces. It's often denoted latex FLN+1 phonetic. FLN+1.
Okay, I think we have all the pieces of the title. We have the MOTIVIC class as our measurement tool, the space of GENUS's zero maps as our complicated object, and the flag variety is the target. We've done a full deconstruction.
I agree. The title primes us for a journey into classifying some very sophisticated geometric objects. I think we're ready for the authors.
All right. The paper is co-authored by 5 mathematicians: Jim BRYAN, BALA ELEK, FREDDIE Manners, George SALAFATINOS, and RAVI VAKIL.
A very strong team.
And it's important to note, right up front, there's an affiliation disclosure in section 1.2. It mentions the involvement of authors who are associated with Google DeepMind.
And that disclosure isn't just boilerplate text. It's a signal that the process of discovery here, it departs from the traditional model of a lone mathematician or a small university group. This new collaborative method is a central and very modern theme of this paper.
That covers the title and the list of 5 authors. Have we missed any initial nuances, perhaps regarding the nature of the mathematics implied by the title?
I think we've established the high-level concepts: algebraic geometry, moduli spaces, and the specific tool used for classification, the growth-endian group. The title primes us for a journey into classifying sophisticated geometric objects. Let's proceed to the abstract.
Abstract.
Okay, diving into the abstract. The very first sentence immediately defines the central players using the notation we've just been discussing.
Yes, the source text says, let latex, FLN+1 phonetic, FLN+1 be the variety of complete flags in latex, AN+1 phonetic, AN+1 in latex X, omega-2 beta FLN+1 be the space of based maps, latex, F math BP1, right arrow, FLN+1 phonetic. F from P1 to FLN+1 in the class of latex, F math BP1 beta phonetic, F star of the class of P1 equals beta.
Okay, a lot to unpack there, but we've seen the pieces. FLN+1 is the flag variety. AN+1 is just the standard defined space it lives in.
And omega-2 beta of FLN+1 is our object of study, the space of maps. That superscript 2 on the omega is very deliberate. It's a nod to a similar object in topology, the double loop space, which is the space of maps from the 2-sphere.
And that subscript beta is critical. It denotes the degree or the class of the map. That condition, if the class of P1 equals beta, that's what organizes these map spaces. It sorts them by how much they twist or wrap around the target space.
I think we've thoroughly unpacked the opening sentence, establishing the 2 main mathematical actors, the flag variety and the moduli space of maps to it, stratified by their degree beta. Let's proceed to the next sentence, which reveals the main finding.
Okay, sentence 2. This is where they deliver the main result.
The source text says, we show that under a mild positivity condition on latex, beta phonetic, beta, the class of latex, omega-2 beta, omega-2 beta of FLN+1 in latex, K0 var phonetic, K0 of var, the growth-endian group of varieties, is given by latex, omega-2 beta GLN times A phonetic. The class of omega-2 beta of FLN+1 equals the class of GLN times A to the A.
And here it is, the punchline. The MOTIVIC class of this unbelievably complex high-dimensional moduli space of functions is equivalent to the class of the general linear group, GLN, times an affine space A to the A.
This is the revolutionary insight. GLN is the group of invertible n by n matrices, a very fundamental, well-understood object. And we know its MOTIVIC class is derived from this beautiful, simple formula, which the class of GLN, latex, GLN phonetic. The class of GLN is given by latex, math BBO phonetic, L to the power of n choose 2 times the product from k equals 1 to n of L to the k minus 1. This formula is standard, and it basically reflects the algebraic structure of doing Gaussian elimination.
And the other piece, the affine space A to the A, is really just a featureless blob of dimension A with class L to the A. The fact that our complicated map space simplifies to this, to just GLN plus a giant blob, it means all the geometric complexity of the maps just cancels out in this cut-and-paste world.
It does. It leaves behind the underlying structure of a fundamental algebraic group. And the theorem requires that mild positivity condition on beta, this is a technical check that we'll see later, is called strictly monotonic. It's a necessary condition to make sure certain vector bundles behave nicely.
Here's where it gets really interesting. We've introduced the main result. The MOTIVIC class is equal to that of the general linear group times an affine space. Have we fully captured the revolutionary nature of simplifying this complex moduli space down to a simple group?
Absolutely. The equivalence is only in the Grothendieck group, meaning they share an Euler characteristic and other motivic invariants, but the result is powerful because it links a mapping space, which is a highly nonlinear object, to a simple algebraic group. Let's move to the methodological note.
Okay, that sets up the main mathematical claim. Now let's address the third sentence of the abstract, which is about how this was discovered.
The proof of this result was obtained in conjunction with Google Gemini and related tools. We briefly discussed this research interaction, which may be of independent interest. However, the treatment in this paper is entirely human-authored.
It's a historical moment embedded right in the abstract of a math paper. The AI helped discover the result, maybe through pattern matching or testing conjectures at a massive scale. But the authors, the human mathematicians, are explicitly taking full responsibility for creating and presenting the rigorous, generalizable proof.
It's a clear statement about methodology. The AI is a brilliant conjecture machine, but the human is still the final arbiter of truth and, the creator of the elegant formal proof.
That completes the abstract, covering the main result and the role of AI in the discovery. Should we highlight any specific connection between the abstract and the upcoming introduction?
Yes. The abstract introduced latex, FLN plus 1 phonetic, FLN plus 1, and the degrees latex, beta phonetic. Beta. The introduction will now formally define these objects, starting with the flag variety. Let's proceed to section 1.
Introduction.
The introduction, then.
Yeah.
It begins, as you said, by formally defining our geometric target, the flag variety, in the very first paragraph.
Exactly. The source text states, let latex FLN plus 1 be phonetic, FLN plus 1 equals GLN plus 1 over B be the complete flag variety which parameterizes flags of quotients. Latex KN plus 1 2 head right arrow and 2 head right arrow E1 phonetic K to the M plus 1 surjects onto EN which surjects onto so on down to E1 where latex EK equals K phonetic. The dimension of EK equals K.
So FLN plus 1 equals GLN plus 1 over B. This defines it as a homogeneous space. You take the general linear group, GLN plus 1, and you factor out the Borel subgroup B, which is usually the group of upper triangular matrices. This gives it a nice, clean algebraic group structure.
And geometrically, a point in the space represents a complete flag of quotients. You start with the whole vector space, k to the n plus 1, and you map it down successively onto smaller quotient spaces, en minus 1, all the way down to e1. The condition that the dimension of ek is exactly k is what makes the flag complete.
So the space itself is a sort of library, organizing all possible ways to create these specific nested structures.
A perfect analogy. That defines the flag variety latex, FLN plus 1 phonetic. FLN plus 1 as both a quotient space and a parameter space for specific vector space structures. Have we missed any details in the definition of the structure?
I think we've established the core concept. It's a space that organizes nested structures. Let's move to the next sentence, which introduces vector bundles over this space.
Okay, the first paragraph continues by defining the intrinsic structure that this variety carries. It says, there is a universal sequence of vector bundle quotients on latex, FLN plus 1 phonetic, FLN plus 1, FLN plus 1, 2 head right arrow, 2 head right arrow, O plus N plus 1 over tech 2 head right arrow, E1 phonetic, O plus N plus 1 over FLN plus 1, which is EM plus 1, subjects onto EN, and so on down to E1.
All right, let's take a moment here to really understand universal vector bundles. This is a key concept. These aren't just abstract chains of vector spaces. They are structured objects that live over the variety latex, FLN plus 1 phonetic, FLN.O plus 1.
Right. A vector bundle is essentially a family of vector spaces that are parameterized by the points of the variety. And this sequence is called universal because for any point x in the flag variety, which remember represents one specific flag, the fiber of the bundle ek that sits over that point x is precisely the k-dimensional quotient space, ek, that's defined by that flag.
So the whole sequence of quotients is organized into these vector bundles, and it all starts from this latex mathematical O plus N plus 1 FLN plus 1 phonetic, O plus N plus 1 over FLN plus 1, which is just the trivial bundle.
The trivial bundle, yes. These universal bundles are the essential infrastructure of the flag variety. Their existence is what allows us to define the degrees of the maps we're interested in.
Okay, let's unpack this. We now have the flag variety carrying a sequence of universal vector bundles. Have we explained why these bundles are important for the maps? We haven't yet, but that's exactly what the next definition, the map space latex, omega-2 beta phonetic. Omega-2 beta clarifies, as these bundles are used to define the degree latex beta phonetic beta. Let's proceed to the definition of the space of maps.
Right. Paragraph 2 brings us back to our central object, latex. Omega-2 beta FLN plus 1 phonetic, omega-2 beta of FLN plus 1, and formalizes the constraints on it.
The text says, let latex omega-2 beta FLN plus 1 be the space of genus 0 base maps in the class latex. Beta phonetic, latex. Omega-2 beta FLN plus 1, latex FLN plus 1, FLN plus 1, FLN plus 1, FLN plus 1, F1 plus 1. FLN's beta FPL F1 plus 1 is the set of maps F from P1 to FLN plus 1, such that F star of the class of P1 equals beta, and F of the point 1, 0 equals the identity element.
Okay, so two constraints defining this space of functions. First, the degree constraint, F star of the class of P1 equals beta. That selects how the map twists the space.
And second, the based map constraint F of the point 1, 0 equals the identity element. This based map condition is so important for the technical side of things, isn't it? It basically fixes the map, forcing it to take a specific point in the domain, which is 1.2 in homogeneous coordinates, to a specific point in the target space, the standard flag, which is denoted I'd.
It is. Without it, the moduli space would be unstable, much less well-behaved geometrically. It would be much harder to study.
That defines the complex space we are studying, latex. Omega-2 beta, FLN plus 1, phonetic. Omega-2 beta of FLN plus 1, including the based map constraint. Any further elaboration needed on the role of the base point?
The base point condition is vital for stability and the boundary behavior of the moduli space. Without it, the geometry is much less tractable. Now let's see how latex beta phonetic beta is quantified.
Right. The complex space is stratified by this degree beta, and it's anchored by the base point. The obvious next question is, how do we actually, measure beta? Paragraph 3 explains this.
It says, there is an isomorphism latex, A1 FLN plus 1, Kangfart ln phonetic. A1 of FLN plus 1 is isomorphic to Zn, such that the n-tuple associated to latex, beta phonetic, beta is given by latex D1 dtext Di equals the degree of F star EI.
So the degree class beta isn't just one number, it's actually a vector of n integers, D1 through Dn.
And those integers are defined by the degrees of the pulled back universal vector bundles. That's the Di equals degree of F star EI part.
Okay, let's elaborate on this pullback concept because it's so important. The map F is going from P1 to the flag variety. So it takes the universal bundle EI, which lives on the flags variety, and it pulls it back to create a new bundle, F star EI, that lives over the much simpler projective line P1.
And the key fact is that vector bundles on P1 are classified entirely by one number, their degree. So Di is simply that degree. The n components of beta are just the n different ways the map F twists the n intrinsic vector bundles on the flag variety. We've established that the degree latex, beta phonetic. Beta is a vector of n integers, latex, D1 dots Dn phonetic, D1 to Dn, defined by the degrees of the pulled back universal bundles. Let's look at the specific condition required for the theorem.
Right. This defines the mathematical quantity that controls the whole analysis. Now, paragraph 4 introduces the crucial prerequisite for the main theorem to even work.
It says, we say that latex beta equals D1 through Dn is strictly monotonic if latex 0 d high n d hen d dus e dus d dots e die up c wars t dot dn phonetic. 0 is less than Dn, which is less than Dn minus 1, and so on down to D1.
In this strictly monotonic condition, this is the mild positivity condition that was mentioned back in the abstract.
Right.
And make sure that all the degrees are positive integers and that they form a strictly decreasing sequence.
Right, and this condition isn't arbitrary at all. It's a structural guarantee. It translates directly into the algebraic world, ensuring that certain vector bundles we construct later in the proof have what are called positive splitting degrees.
And that positivity is what simplifies the counting processes in the Grothendieck group that make the proof possible.
So strictly monotonic is the key condition for the main theorem to hold. Let's formally state that main theorem now.
Perfect. We are now fully equipped to read Theorem 1.1 again, but this time with all the terms defined with full precision.
Okay, Theorem 1.1. Suppose latex beta equals D1 to Dn is strictly monotonic. Then we have the following equality in latex. K0 vark, phonetic. K0 of vark, the Grothendieck group of varieties over latex. K phonetic, omega-2 Dn, ELON plus 1, ELN times math, BAD, N2, phonetic. The class of omega-2 Dn to D1 of FLN plus 1 equals the class of GLN times A to the D minus N squared, where latex D sum K1 2 dk phonetic. D equals the sum from K equals 1 to N of 2 dk.
And the proof is essentially a long, beautiful demonstration that the cut and paste complexity of that left side perfectly matches the clean simplicity of the right side, with the dimension of that affine space being dictated by that exact formula for D.
This is the centerpiece of the paper. We now have the precise algebraic statement, including the formula for the exponent D. Let's analyze the immediate consequence mentioned next.
Right, the immediate practical consequence, which comes in paragraph 5.
It says, in particular, Theorem 1.1 gives an equality of point counts over finite fields. See corollary A.1.
And this is where the magic of the MOTIVIC class really shines. If two things are equal in the growth-ending group, it means their Euler characteristic must be the same. And if you're working over a finite field, the number of points on them has to be identical.
Which is exactly how the AI first discovered this result. It was likely done by matching experimentally determined point counts of the complicated variety on the left with the known simple counting formula for GLN on the right.
Okay, we've established the precise algebraic statement and its initial verification through point counting. Let's now pivot to the bigger picture, the larger scientific motivation, which is the connection to topology.
Let's do it. We've covered the core statement of the theorem. Now we get to the why.
Topological context, paragraph 6.
Paragraph 6. This is where the paper sets up the high stakes of this research. It defines our algebraic variety as an approximation of a really key object in topology.
The text reads, our original interest in the variety latex, omega 2 beta, FLN plus 1, phonetic. Omega 2 beta of FLN plus 1 is as an algebraic counterpart to the double loop space in topology. Latex, omega 2 beta top of FLN plus 1 equals the set of maps from S2 to FLN plus 1, where we take latex, FLN plus 1 phonetic. FLN plus 1 over the complex numbers with the complex analytic topology.
The double loop space. So the topological double loop space, omega 2 top of X, is the space of all continuous maps from the two-sphere S2 to some target space X. Our algebraic variety, the one we've been talking about, is an extremely specific, rigid subset of this massive space.
Exactly. And the connection between that small algebraic subset and the full topological space is what validates this whole line of research. The paper cites a major result, the Boyer-Hurtubise-Mann-Milgram theorem, or BHMM theorem.
And the key sentence here is, there is a natural inclusion latex omega 2 beta, or omega 2 beta top, omega 2 beta of FLN plus 1 includes into omega 2 beta top of FLN plus 1, and by a theorem of Boyer, Hurtubise, Mann, and Milgram. The above map is latex K of beta connected, where latex K beta right arrow 50 phonetic, K of beta goes to infinity as latex beta right arrow and 50 phonetic, beta goes to infinity in a suitable sense.
So K of beta connectedness. What that means is that the small algebraic variety captures the shape of the full topological space perfectly up to a very high degree. Specifically, the inclusion map induces an isomorphism on all the lower homotopy groups, pi I, for I less than K of beta.
And as the map's degree, beta, gets larger and larger, this number K of beta goes to infinity. So the algebraic space becomes a better and better, more accurate topological approximation of the full double loop space.
The implication is clear. If we can understand the algebraic variety for large degrees, we've essentially solved the much harder topological problem.
That sets up the high stakes. The algebraic variety approximates the complex topological space. Have we fully captured the implication of the degree beta growing large?
Yes, the larger the degree, the more the algebraic space resembles the topological one.
Now let's explore what the topological space is known to be equivalent to.
Okay, so what is the topological target? What are we trying to approximate? Paragraph 7 provides the first topological equivalence. It says, by elementary homotopy theory considerations, there is a homotopy equivalence latex, omega 2 beta top, FLN plus 1, phonetic. Omega 2 beta top of FLN plus 1 is homotopy equivalent to omega 2 top of UN plus 1 for every latex beta phonetic beta.
So the full topological double loop space of our flag variety is equivalent in shape. It's homotopy equivalent to the double loop space of the unitary group U1 plus 1.
Right. And then paragraph 8 takes us to the ultimate geometric ideal. It says, the rational homotopy type of the double loop space is known. Latex, omega 2 top, U1 plus 1, Ketum plus 1, simic U, M plus 1. Omega 2 top of U1 plus 1 is rationally homotopy equivalent to UN.
Okay, so the double loop space of U1 plus 1 is rationally equivalent to the unitary group of one dimension lower, UN. And rationally equivalent just means they share the same homotopy structure if you ignore some subtle effects called torsion.
Precisely. So the long-standing conjecture in this field has been that the algebraic variety we're studying should mimic this topological result. Paragraph 9 poses this as the central research question.
The main topological question.
Yes, question. How does the rational homotopy type of latex, omega 2 beta FLN plus 1, phonetic, omega 2 beta of FLN plus 1 compared to the rational homotopy type of latex, UN, phonetic? UN.
So the topological expectation is that latex omega 2 beta top FLM plus 1 phonetic omega 2 beta top of FLM plus 1 should behave like latex UN phonetic UN. This leads directly to the primary topological question of the paper.
I think we've covered that well. Let's look at the context for that question.
This question is what frames the entire utility of Theorem 1.1. Does the algebraic answer we found GLN times an affine space, which is topologically related to UN, does it actually reflect the true homotopy type?
Paragraph 10 provides some important context. It says, yes, in the simplest, minimal, strictly monotonic case, where beta is just n1, previous work had already shown that the variety is actually isomorphic to GLN times c to the n, which does have the expected homotopy type of UN.
So it works for the simplest case.
Right, which makes the bombshell in paragraph 11 all the more significant. It says, and I'm paraphrasing here, even though it works for the minimal case and for infinitely large degrees, there are finite, non-minimal cases where it fails, where the algebraic space does not have the homotopy type of UN, not even rationally.
Wow. Okay, so that's a critical finding. The main theorem, the MOTIVIC class, the cut and paste composition is always correct. But the stronger geometric requirement, the actual shape or homotopy type, can fail for specific finite degrees.
Exactly. This divergence is mathematically profound, and paragraph 12 shows how the main theorem still provides powerful evidence for a connection. Equality in the Grothindia group means the weight polynomials are equal. This strongly suggests the spaces are highly similar, which prompts the authors to make one final optimistic conjecture.
Conjecture 1.2.
Conjecture 1.2. It states that the inclusion map should induce an isomorphism of the rational cohomology rings, so that latex, EBQ beta FENM plus 1 math VAQ, math BBQ bound from HUN, phonetic. H star of omega 2 beta of FLN plus 1 with Q coefficients is isomorphic to H star of UN with Q coefficients.
And if that were true, this cohomology isomorphism would be a powerful bridge. It would show that the algebraic variety captures the fundamental structure of the unitary group, even if it fails the stricter homotopy test in some cases.
We have completed the motivational material, establishing that the MOTIVIC class calculation is a key step towards resolving a major question about the relationship between algebraic and topological loop spaces. Let's move on to related work.
1.1, relate.
Okay, section 1.1, related work. Paragraph 14 here just acknowledges the academic lineage. It confirms that this work, stands on the shoulders of giants like Seagal and Kirwan.
And it also notes that it generalizes existing techniques that were developed for maps into simpler spaces, like Grassmannians, in work by Farb and Wolfson.
So the field is well established, and these authors are pushing the boundary by moving from those simpler partial flags, the Grassmannians, to the full, complete flag variety.
Exactly. That puts this work into its proper context, generalizing previous results. Now for the truly unique section.
1.2, the role of AI in the results of this paper.
Right. Now for the narrative of the discovery. This is really fascinating. Paragraph 15 begins by establishing human authority, and they are very clear about this.
Very. It says, we should first emphasize that the text of this paper was written from scratch by the authors. In particular, the authors are responsible for the correctness of the arguments presented here in the usual way.
A really critical statement of accountability, especially in this new era of mathematics.
Then paragraph 16 names the specific systems that were used. Google Gemini, DeepThink, and a specialized internal system they provisionally named Foolproof. This grounds the claim in specific, powerful research tools.
And paragraph 17 details the initial process. The authors started with the easier, weaker problem, the point counting result, which is corollary A.1. They used traditional computational tools like Macaulay 2 to gather a bunch of numerical evidence suggesting the result was probably true.
But the critical methodology was what they call the scaffolding. They broke the big generalized problem into a series of hierarchical subproblems. Then they fed them to the AI system, often annotating the later steps with the AI's own successful solutions to the earlier ones.
It's a pedagogical approach, really. You're teaching the AI how to think about the problem.
You are. And it's essential because, as paragraph 18 reveals, the AI systems initially hit a wall. It says, none of the systems used has successfully proved corollary 8.1 without assistance. It could not generalize them to the full problem.
So the AI could solve a specific case, but that leap to the general proof was still out of its reach. This really confirms the necessary role of human intuition.
It does, and paragraph 19 describes the breakthrough moment. A close human analysis of the AI output isolated key intermediate statements which the human mathematicians could see how to generalize, thereby suggesting a proof strategy for the general case.
So the AI provided a correct, detailed path for a special case, and the human mathematicians recognized the universal principle that was embedded in that path. That's the synthesis step that defines this new kind of partnership.
Right, and then paragraphs 20 and 21 detail the final success. Once the AI was reprompted with questions that hinted at this correct human-derived strategic approach, it successively generalized the argument. It proved the full point-counting result and then the full MOTIVIC class statement, Theorem 1.1.
So the AI served as this unparalleled executor and rigorous verifier once the strategic insight was provided by the humans.
And paragraph 22 acknowledges the quality of the AI's raw mathematical output, noting that some of the proofs generated by foolproof were, in their words, already very accomplished.
Then paragraph 23 addresses the big question of novelty. Was the AI just regurgitating things from its training data? And they conclude that the AI's contribution involved a genuine combination of synthesis, retrieval, generalization, and innovation, especially since the systems were run offline without access to the internet.
This is a landmark moment. This entire section provides a meta lesson on modern mathematics. The human is still needed to provide the overarching strategy, but the AI is an unparalleled partner for complex execution and generalization. Have we extracted all the lessons from this collaboration?
I think so. It's a clear model of assisted discovery. Now, having established the theorem, its motivation, and its genesis, we must move into the proof itself, starting with acknowledgments. Okay, section 1.3 is brief. Paragraph 24 just provides the necessary thanks, acknowledging Google DeepMind for their extensive support and collaboration, and noting specific support from the Blueshift team.
That handles the required things. We are now ready for section 2.
With the context established, we transition to section 2, the proof of the main result.
2. Proof of the main result.
Okay, the core mathematical strategy here is decomposition. Section 2.1 establishes the framework for this, breaking the problem down into what they call a tower of simpler fibrations.
Yes, let's get into it.
2.1, partial flags and a tower of fibrations.
Paragraph 25 introduces the general mechanism for this decomposition. It's the partial flag variety, denoted latex, FLN plus 1K phonetic, FLN plus 1 comic.
And this variety parameterizes flags that stop at the kth step. So the quotient sequence runs from Vn down to Vk. It's an incomplete flag.
That's right. And then they define projection maps. Latex, FLN plus 1K, right arrow, FLN plus 1K plus 1 phonetic, FL-N plus 1 comma K plus 1. These are created by simply forgetting the smallest quotient space, EK.
So we're building a stack of geometric spaces, each one a bit simpler than the one below it.
And we confirm the endpoints of this stack. Latex, FLN plus 1 phonetic. FLN plus 1 comma 1 is our original full flag variety, and latex, FLN plus 1N and plus 1 phonetic. FLN plus 1 common plus 1 is just a single point. This tower of projections is what will allow us to decompose the class calculation into n iterative steps.
We've introduced the generalized partial flag variety, which forms the basis for breaking down the problem into manageable steps, defined by the maps LAX, FLN plus 1K, right arrow, FLN plus 1K plus 1 phonetic, FLN plus 1 comma to FLN plus 1 comma K plus 1. Let's examine the universal bundle sequence on these partial flags.
Okay. Paragraph 26 just confirms that the corresponding universal bundle sequence exists on these partial flags, just like on the full flag variety.
And then paragraph 27 generalizes the space of maps, latex, omega 2dn, FLN plus 1K, phonetic, omega 2dn 2dk of FLN plus 1 comic to these new partial flag varieties. They're still stratified by the degrees and constrained by a base point.
Then we get to equation 1, which formally defines the tower of fibrations. It's a map, latex fic, omega 2dn plus 1k, right arrow, omega 2dn plus 1k plus 1 omega FLN plus 1k phonetic unpick from omega 2dn to dk plus 1 of FLN plus 1 comma k plus 1.
And if we can determine the motivic class of the fibers for each of these projection maps, pick, then the total class will just be the product of all those fiber classes.
Exactly. The entire massive problem now reduces to a single, more manageable goal, calculating the motivic class of the fiber of pick.
We have established the structure of the proof, analyzing the tower of maps latex, phonetic pick. If we can understand the class of the fibers of latex, phonetic pitek, we can calculate the class of the entire tower. Now we must define the special spaces related to sections of vector bundles.
Right, and this requires defining some special spaces related to sections of vector bundles. This is definition 2.1.
Definition 2.1 introduces 4 spaces of sections for a generic vector bundle F over P1, all defined relative to some projectivized base point P.
First, we need latex, sigma F, phonetic, sigma of F, which is the projectivized space of all non-zero global sections. And then we have latex NF, phonetic, N of F, which is the subset of those sections that never vanish anywhere on P1.
Then we add the base point constraint, latex sigma phonetic. Sigma P of F requires the section to pass through the specific base point P at the point 1.0.
And finally, the most restrictive space, which is our target, latex, NPF, phonetic. These are the based, nowhere vanishing sections.
We've defined the 4 spaces of sections, the quantity latex, NPF phonetic. NP of F is the most restrictive, and, as we will see, it is exactly the geometric object representing the fiber of our projection map, latex, phonetic.peak.
And lemma 2.2 confirms that this is exactly what we need. It gives the isomorphism that reduces the problem to this section space. The fiber, latex, pi1kf, phonetic. The fiber pi k inverse of F is isomorphic to latex, nvk plus 1, dk plus 1, phonetic. And sub ek plus 1 of ek plus 1 twisted by dk minus dk plus 1.
So the fiber is the space of based, nowhere vanishing sections of a very specific twisted vector bundle. You take the bundle ek plus 1 from the flag and you twist it by a line bundle whose degree is dk minus dk plus 1.
And because of our strictly monotonic condition on beta, that difference in degrees is positive. So that's a positive twist.
And just to briefly recap the logic for why this is true, a point in the fiber corresponds to a choice of refinement, which means choosing a rank 1 kernel. The constraints on that kernel, its degree and base point, translate precisely through some algebraic twisting into the conditions for a based, nowhere vanishing section of that specific twisted bundle.
We've established that the fibers of the tower are classified by the algebraic geometry of based, nowhere vanishing sections of a specific twisted vector bundle. The entire problem now reduces to finding the motivic class of this space, latex, NPF, phonetic, NP of F.
Proposition 2.3, motivic class of NPE.
We've successfully translated a problem in map spaces into a problem in counting sections of vector bundles. The next step is proposition 2.3.
And this proposition is the algebraic breakthrough. It's the formula for the motivic class of that fiber space, NP of E.
Okay, what does it state?
It states, suppose that latex E right arrow mass D1 phonetic. E to P1 is a vector bundle of rank latex R phonetic R and degree latex D phonetic D. And suppose that latex H1E to SUT2 phonetic, H1 of E twisted by -2 is 0. Equivalently, that latex E Kong Bigo plus phonetic. E is isomorphic to the direct sum from I equals 1 to R of OP1 of AI, where latex E key 1 phonetic AI is greater than or equal to 1. Then for any base point latex P phonetic, the class of latex, NPE phonetic, NP of E is given by latex, NPE plus 1 unphonetic. The class of NP of E equals L to the D minus R plus 1 times L to the R minus 1 minus 1.
Wow, okay, so that condition, AI is greater than or equal to 1, ensures all the splitting degrees are positive.
And the key takeaway here is that the result, the class, depends only on the total rank R and the total degree D of the bundle. It does not depend on the individual AIs, the specific way the bundle splits.
That independence is what makes the final proof possible. And the proof itself relies on a beautiful algebraic technique, Mobius inversion in the Grothendieck group.
Let's walk through that proof. What's step 1?
Step 1 is to calculate the class of the larger, simpler space, sigma p of F, the based non-zero sections. By analyzing the constraints on the section's coefficients at the base point, the authors proved that this space is motivically trivial. It's isomorphic to an affine space, latex, math BBF phonetic, A to the degree of F. So its class is just latex, math BLD phonetic, L to the D.
Okay, that's a nice simple start. Step 2.
Step 2 is stratification. We partition the space sigma p of F based on the degree k of the greatest common divisor of the section's component polynomials.
And step 3, this is the crucial one, right?
It is. When you restrict the stratification to the base point p, the strata simplify beautifully. Each stratum, the set of sections where the GCD has degree k, is isomorphic to latex. NPF k times mathematic. NP of F twisted by minus k times A to the k.
Then step 4 is the Mobius inversion setup. The total class is the sum of the classes of these strata. So latex sigmap F. The class of sigma p of F equals the sum from k equals 0 to infinity of the class of NP of F twisted by minus k times L to the k.
And the trick is to isolate the k equals 0 term, which is the class of NP of E that we actually want. This is done by calculating the expression latex, sigmap E, phonetic. The class of sigma p of E minus L times the class of sigma p of E twisted by minus 1.
And step 5 executes that final clean calculation. Using the result from step 1, the formula becomes latex. Math BOLD, math BLD, L to the D minus L times L to the D minus R, which factors perfectly into the claimed result. The fiber class is solved.
We've finished the deep dive on the MOTIVIC class of the fiber, relying on that beautiful Mobius inversion trick in the Grothendieck group. The class is known independent of splitting type. Now we apply this back to our tower of fibrations.
So that's the algebraic engine of the proof. We know the fiber's MOTIVIC class is constant, and we have a formula for it.
And Remark 2.4 then confirms that the strictly monotonic condition on beta was necessary all along. It prevented the result from depending on complicated interactions between the base point and any non-positive bundle Simons.
This justifies the necessity of the strictly monotonic condition on latex, beta phonetic, data, because that condition translates precisely into ensuring the bundles we analyze have positive splitting degrees, which in turn simplifies the geometric calculation of the fibers.
Exactly. Now we just apply this formula in corollary 2.5 to calculate the fiber class for our specific problem.
And what does that corollary state?
Corollary 2.5 states, if latex dnd.d.d1 phonetic dnd.dn is less than dn minus 1 and so on, then for all latex f phonetica f, the fiber's latex pi 1k inverse of f, the phi 1k 1 phonetic, the class of the fiber equals L to the power of k plus 1 dk plus 1 minus k times L to the k minus 1, independent of latex f phonetic f.
So the critical result is that the class is constant. We have the rank f caret k plus 1 and the total degree d equals k plus 1 d, k plus 1 dk minus k dk plus 1. Plugging those into the formula from proposition 2.3 gives this exact result.
This is the second crucial component of the proof. Calculating the exact class of the fiber, latex, pi 1k, f phonetic, the class of pi k inverse of f. If the projection latex phonetic pick were a Zariski locally trivial fibration, we'd be done. But we need one more definition.
We know the fiber class is constant, but then paragraph 31 injects a geometric hurdle.
A big one. It says, if latex pick phonetic were a Zariski locally trivial fibration, we could immediately relate the classes. However, it is not. The fibers need not even be isomorphic as varieties, as shown in example 2.0 below.
So the varieties themselves might actually change shape over the base space, even though their cut and paste composition is the same. The standard definition of a fibration fails.
Which means the authors had to innovate. This leads to definition 2.6. The motivically trivial fibration, this is a weaker condition. It says the base space X can be partitioned into strata, and over each stratum the map is a locally trivial fiber bundle, and crucially, only the motivic class of the fiber has to be constant across the strata.
The fibers themselves don't have to be isomorphic, just their class in the Grothendieck group.
And this weak condition is exactly enough to let us use the formula y equals x times f in the Grothendieck group.
This is the formal tool that connects the calculation of the fibers class, corollary 2.5, to the class of the total space. Now we state the proposition that allows us to proceed.
Right. And proposition 2.7 asserts that our map, peak, is a motivically trivial fibration, and it relies entirely on that constant fiber class result we just saw. So now we just need to prove the local triviality required for this proposition to hold.
Assuming proposition 2.7 is true, we trust the authors for now, we'll cover the proof later, we can now execute the final inductive calculation.
Let's do it.
2.3. Motivically trivial fibrations.
Continued. Okay, so to prove proposition 2.7, we need to show local triviality. Paragraph 38 outlines the stratification criteria for the base space. What are they?
There are two. First, the bundle's isomorphism type, meaning its splitting type, which we'll call R. And second, the depth of the base point within the filtration that's induced by that splitting, which we'll call L.
And the proof of local triviality relies on this concept of special groups, defined in paragraph 39. What makes a group special?
An algebraic group G is called special if all principal G bundles are Zariski locally trivial. Basically, if the algebraic group that controls the automorphisms of your bundle is special, you get local triviality automatically.
Which is exactly what we need for our definition of a motivically trivial fibration.
Right. And paragraph 40 confirms that the automorphism group of the general vector bundle, FRR, is an extension of special groups, so it is itself special.
And paragraph 42 confirms the really critical fact. The stabilizer subgroup that fixes the base point behavior is also a special group.
It is. So then paragraph 43 defines the final stratum of the base space, stratified by both the bundle type R, A, and D, the base point depth L.
We've now rigorously defined the stratification based on bundle isomorphism type and base point behavior. Critically, we established that the relevant automorphism groups are special. This is the necessary input for lemma 2.8.
And lemma 2.8 confirms the local triviality over each of these strata. The proof uses the fact that the space of augmented flags is a principal bundle for that special stabilizer group. Since the group is special, the bundle is locally trivial, and that proves proposition 2.7.
We have now closed the loop. The use of special algebraic groups allowed us to prove that the constant fiber class property implies the MOTIVIC triviality condition, which in turn validated the grand calculation of Theorem 1.1. We now proceed to the cautionary examples.
Well, first we finish the calculation itself.
2.2, finishing the proof of the main theorem, actual calculation, Kant.
Right. We return to the calculation, now fully justified. Paragraph 34 sets up the induction. The total class is the product of the fiber classes.
So the total class is the product from k equals 1 to n of latex. Math BBL plus 1 dk k dk plus 1 k plus 1 k dk plus 1 k minus k times L to the k minus 1. We need to solve for the exponent of L, which they call alpha.
So latex alpha, k plus 1 dk, k dk plus 1 k phonetic. Alpha equals the sum from k equals 1 to n of k plus 1 times dk minus k times dk plus 1 minus k.
And the key trick here is to do an index shift on that middle summation term, the one with dk plus 1. It simplifies to the sum of k1 times dk.
So when you combine the dk terms, you get the sum of k plus 1 dk minus k1 dk, which collapses beautifully to just the sum of 2 dk. And that is exactly d. Exactly. The final exponent alpha is just d minus the sum of k, which is the binomial coefficient n plus 1 choose 2. So latex alpha d binom n plus 1 2 phonetic, alpha equals d minus n plus 1 choose 2. The complex calculation collapses to the simple term latex, d binom n plus 1 2 phonetic, d minus n plus 1 choose 2. This confirms the latex math BBL alpha phonetic, L to the alpha factor in our final MOTIVIC class. Now we relate the remaining product to latex, GLN phonetic, GLN. Right. Paragraph 35 recalls the class of GLN, which we saw earlier. It's latex, GLN, math BBL is phonetic. The class of GLN equals L to the n. Choose 2 times the product from k equals 1 to n of L to the k minus 1. So paragraph 36 executes the final substitution. Our result is L to the alpha times the class of GLN divided by L to the n choose 2.
Which means the final exponent on L is latex. D binom n plus 1 2 minus n choose 2. And the sum of those two binomial coefficients is just n squared. So the final exponent is d minus n squared.
Resulting in the final formula. Latex, omega 2dn, OD1, FLN plus 1, GLN times math, BBA, DN, 2 phonetic. The class of omega 2 dn 2d1 of FLN plus 1 equals the class of GLN times a to the d minus n squared. Theorem 1.1 is proven.
The core calculation is complete, demonstrating how the product of the fiber classes combined with the standard formula for latex GLN phonetic, GLN, precisely yields the main theorem. The structure of the proof now demands that we provide the deferred proof of proposition 2.7. Well, we've already covered it, so now it's time for the examples.
2.4, negative examples.
Okay, this section, it's so important because it emphasizes the critical distinction between having the same MOTIVIC class and having the same actual geometric shape.
It really is. Example 2.9 shows the failure of rational homotopy for the case n equals 1 and d equal 2. The MOTIVIC class calculation is correct, and it suggests the shape should be like U1, which is just a circle, S1.
But the actual geometry shows that the space, omega 2 2 of P1, is a non-trivial bundle over the real projective plane, RP2.
Right, and since its second homotopy group is non-zero, it can't be rationally homotopy equivalent to a circle whose second homotopy group is 0. So the algebraic result is perfect, but the geometric reality is more complicated, at least for some of these finite degrees.
This negative example is critical. It shows that while the cut-and-paste structure, MOTIVIC class, works out perfectly, the delicate topological structure, homotopy type, can fail even for small, strictly monotonic degrees.
And example 2.0 is what explains the necessity of that motivically trivial fibration definition. The authors show that for NO2, depending on the splitting type of the bundle E2, the fiber variety can be demonstrably non-isomorphic to itself over different points in the base.
So the fibers actually change shape. This confirms that the mat pick is not a fibration in the strict sense.
And it confirms that relying on the constancy of the MOTIVIC class was the only way to save the proof.
This beautifully concludes the mathematical section, showing why the authors had to invent the tool of motivically trivial fibrations. The math simply wasn't strong enough for standard fibrations, but the MOTIVIC class saved the day.
It really is a beautiful piece of work.
Appendix A, detailed discussion of use of AI.
So Appendix A revisits the narrative of the AI collaboration. Paragraph 47 recalls the AI's initial target, which was the point counting result, corollary A.1.
And paragraph 48 details that sequence of events again. The AI solved special cases, it identified that key intermediate step about the independence of splitting type, and then the human researchers generalized that observation into the foolproof strategy.
Paragraph 49 confirms that once the human researchers hinted at the correct structural approach, the AI successfully executed the proof for the point counting and then generalized it to the full motivic statement.
And paragraph 50 adds that intriguing detail. The AI was later asked to investigate the homotopy property of the fiber, and it successfully generated the counterexamples we just discussed, the ones that define the boundaries of the theorem's applicability.
Appendix A confirms the iterative, guiding nature of the collaboration, showcasing the AI's ability to execute a strategy once the human identifies the correct generalization.
A perfect summary.
Appendix B. Example prompts.
Appendix B then gives concrete evidence of this scaffolding process. Prompt 1 is the initial warm-up, asking for small case calculations.
Prompt 2 pushes for the generalization for N2.
And prompt 3 is that critical intervention. It explicitly asks the AI for the number of points in the fiber over a fixed point, which is what steered the AI toward the whole tower decomposition and fiber analysis strategy.
The prompts reveal the scaffolding process used to guide the AI, demonstrating the pedagogical approach required to extract mathematical proofs from these systems.
Appendix C, example AI outputs.
And finally, Appendix C showcases the technical rigor of the foolproof system. The solution it generated for the N2 case is just incredible. It involves translating the geometry into counting polynomial triples over a finite field.
And it correctly used extremely specialized counting techniques, including the polynomial Mobius function and the polynomial zeta function. This isn't trivial stuff.
The final result was derived using the structural insight that the count depends only on the degree of the first triple and then isolating the final answer via two-variable Mobius inversion formula. It really confirms the AI's capacity for rigorous, highly technical mathematical execution.
It's a glimpse into the future, really.
References and emails.
This final example confirms the computational prowess of the AI system, specifically foolproof, showing its ability to generate rigorous, highly technical mathematical proofs involving polynomial rings over finite fields, index shifting, and specialized counting methods.
We have now processed every title, author, abstract, section, subsection, paragraph, sentence, and formula in the provided source material, including the necessary explicit checks and foundational deep dives required by the protocol. We have successfully derived the full path to Theorem 1.1 and understood the revolutionary context of its AI-assisted discovery.
The paper concludes with 14 cited works, confirming its place in the established lineage of algebraic geometry.
And for complete transparency, the affiliations and email addresses of the 5 authors are provided. Outro.
This has truly been a deep dive into the intersection of abstract algebra and, well, the future of discovery. The mathematical simplicity of Theorem 1.1, the idea that the complex space of maps to the flag variety shares the cut-and-paste blueprint of the general linear group, it's just startling.
It is, and the meta-story is just as profound. This new model for progress, human intuition guiding the AI's rigorous execution, overcoming the model's limitations through strategic scaffolding, it's a new way of doing mathematics.
So we'll leave you with the puzzle that the authors themselves established. The MOTIVIC equivalence is proven. But the paper also showed that the stronger topological equivalence fails for some small degrees. This means the spaces are algebraically the same, but topologically different in subtle ways.
So if the algebraic class is so beautifully simple, yet the geometric shape sometimes diverges, what is the unknown geometric feature that differentiates the two? Is there some non-obvious deformation that could reconcile the spaces and prove conjecture 1.2 for all degrees? Or is this divergence between motivic simplicity and topological complexity just an unavoidable law of nonlinear geometry?
Something to think about. Until next time. Welcome back to the deep dive. Today we are taking on a truly monumental paper. It's titled The Motivic Class of the Space of Genus 0 Maps to the Flag Variety.
It's a beast, authored by BRYAN, ELEK, Manners, Salafatinos, and VAKIL. And what it does is it takes one of the most complex objects you can imagine in algebraic geometry and boils it down to something almost shockingly simple.
Exactly, a phenomenal result. But what makes this deep dive for us so essential is not just the result, but the story of how it was achieved. This wasn't just a bunch of mathematicians at a blackboard.
No, not at all. This was a deep iterative collaboration between, some of the top minds at places like Stanford and UBC and the advanced AI systems over at Google DeepMind. We're going to be dissecting both the math and what this collaboration means for the future of discovery itself.
So that's our mission today. We are going to proceed with extreme granularity, following our unabridged protocol. We're going to go line by line to understand this fundamental breakthrough, how a complex, sort of infinite dimensional space of functions gets reduced to a simple formula involving the general linear group.
And to do that, you have to start at the absolute beginning. You have to start with the title.
Right. That first crucial phrase, MOTIVIC class.
Yes. This is everything. Before we can even talk about the maps or the flag variety, we have to understand what this means. The term MOTIVIC class tells you that we're not working with the geometric objects themselves, but with their representations in a very special algebraic structure.
And that structure is called the growth-endic group of varieties, which is usually denoted with the symbol $var, co-not of var.
Right. And you might be asking, why? Why invent this incredibly abstract sounding thing? What problem does it actually solve?
I think that's the perfect question. Why not just study the varieties directly?
Well, because geometry is, to put it mildly, messy. Varieties, which are, just the solution sets to polynomial equations, they can have incredibly complicated shapes, topologies, all sorts of intricate structures. If you try to compare two of them directly, it's often an impossible task.
So you need a way to simplify, a way to ignore some of the complexity to see a deeper structure.
Precisely. The growth-endic group is built on a simple, powerful idea that you might call cut and paste. Imagine you have a variety, let's call it Zix. Now find a nice, well-behaved piece inside it, a closed subvariety, let's call it Zirl.
Okay, so like a line drawn on a plane.
A perfect example. The plane is Zixel, the line is Zirl. The growth-endic group has one fundamental rule. The class of the whole thing, 6 egallers, must be equal to the class of the part you cut out, Zirl, plus the class of what's left over, which is the open complement, sexset minus zir.
The plane minus the line.
Exactly. So plane line plus plane set minus line. This rule, this cut and paste or scissor congruence, lets you break down any complicated variety into simpler pieces and just add up their representatives, their classes. It's a way of doing arithmetic with shapes.
So you're losing the specific geometric information about how the pieces were glued together, but you're gaining a way to count.
That is the ultimate payoff. This whole structure is designed to connect back to something very concrete, counting points over finite fields. If you have a variety defined over, say, the integers, you can ask how many solutions your polynomials have over a finite field of math BBFQ.
And this growth-endic group, this $var, it encodes that information.
It does, through a special element in the ring. This element is called $. It's defined as the class of the simplest variety imaginable after a point, the affine line. So $, math BEA1K$ equals the class of A1K.
The affine line, which is just a line.
It's just a line. Over a finite field math BVFQ, how many points are on that line?
Tar points.
Right. So when you do all your abstract calculations in this ring using the symbol $, and you finally get a polynomial, say, $6 equals L2 plus L2, you can turn it into a concrete number. You just substitute dollars with 2. The number of points on your variety, $6 over math BBFQ, would be $2 plus Q.
I see. So the MOTIVIC class is like a universal formula for counting points, and the whole point of this paper is to find that formula for a very, very complicated space.
That's it, exactly. The title is a giant signpost saying, we are going to ignore the messy topology and focus on the combinatorial, countable essence of this object.
Okay, so that covers the analysis of the paper's title and provides the necessary foundational context for the growth-endic group. Have we missed any nuances in the title's implications?
I think we've thoroughly unpacked it. The key takeaway is that we're in a world of algebraic simplification where the goal is a polynomial in dollars.
Let's proceed to the authors.
Right, the author list. We have BRYAN, ELEK, Manners, SALAFATINOS, and VAKIL. It's a mix of academics from, UBC, UNSW, Stanford, and Google DeepMind. And that's the other crucial piece of framing. The inclusion of FREDDIE Manners and George SALAFATINOS from DeepMind is a deliberate signal. It tells you right away that the process of discovery is going to be as interesting as the result itself. It foreshadows the AI section.
It sets the expectation for something new in terms of methodology.
It absolutely does.
So the author list is covered. Shall we move to the abstract?
Let's proceed sentence by sentence through the abstract. This is where they lay out the main players and the central claim.
All right. Sentence 1 introduces the core geometric objects. First, the flag variety, which they denote FLN, plus a dollar.
Right. Pronounce the flag variety FLN plus 1. This is the space we're mapping into. So what is it? A complete flag in a vector space, say O1 plus 1 a dollar, is a nested sequence of subspaces.
So you have a one-dimensional subspace sitting inside a two-dimensional one, which sits inside a three-dimensional one, and so on, all the way up to the full space, like a set of Russian dolls, but with vector spaces.
Perfect analogy. The flag variety, faith ln plus some 1, is the space that parameterizes every single possible way you could choose such a nested sequence. It's a beautiful, highly structured geometric object in its own right.
And the second object is the one they're actually studying, the space of based maps, which they write as omega 2 beta FLN plus 1.
Which we'd say out loud as omega squared sub beta of FLN plus 1. This is the space of all well-behaved functions, specifically rational maps, from a simple space into that complicated flag variety.
The simple space is the projective line, math.FLN.
Yes. The map is written $5. Maps can be 1 to FDLN plus LM1F maps from the projective line P1 to FBLN plus 1. Topologically, you should just think of math BP1 as a sphere. So we're studying maps from a sphere into this flag variety. The notation omega 2 is actually borrowed from topology, where it means double loop space, which is exactly the space of maps from a 2-sphere.
And these maps have constraints. They can't just be any old function. They have a fixed degree, which is given by this subscript beta.
Right. That's the condition SMASMATH ape star of the class of P1 equals beta. This is a bit technical, but you can think of beta of S as a collection of numbers that tells you how many times the map wraps around different parts of the flag variety. It fixes the complexity of the functions we're looking at.
So for a given complexity beta B, you get a specific space of maps.
A very specific and usually very complicated space of maps.
Okay. That covers the first definition in the abstract. Have we missed any nuances?
We've thoroughly unpacked it. We have the target space, the flag variety, and the object of study is the space of maps into it. Moving to the main claim.
And what a claim it is. The second sentence is the main result. It reads, omega 2 beta FLN plus 1 GLN times AS.
Right. And for the TTS, that's the class of omega squared sub beta of FLM plus 1 equals the class of GLN times the affine space A to the A. This is the core of the entire paper.
It's just a stunning simplification. On the left, you have this incredibly complex space of functions parameterized by polynomials. On the right, you have something we know and love from basic linear algebra.
Well, almost. First, we need to remember we're talking about their classes in K0 of var. We're not saying the spaces are identical, just that their algebraic shadows are.
And the components on the right are what exactly?
GLOE is the general linear group. It's the group of all invertible line dollars times EL matrices. It's a fundamental object in mathematics. And A to the A is just an affine space of some dimension of R. From a MOTIVIC perspective, affine space is the simplest thing there is. Its class is just law Euler. It's algebraically uninteresting.
So the theorem is saying that all the rich, complicated structure of this map space, when viewed through the lens of Taylor's var, boils down entirely to the structure of the general linear group, plus some fluff from the affine space.
That's a great way to put it. All the complexity just cancels out, leaving behind one of the most fundamental groups in all of mathematics. It's an algebraic miracle.
The central finding is covered. Any rhetorical purpose left to address here?
The sentence clearly establishes the main achievement. It's the punchline. Let's proceed to the methodological note.
Right. The final sentence of the abstract. The proof of this result was obtained in conjunction with Google Gemini and related tools.
This is a bold statement to put right in your abstract. They are being upfront about the non-traditional discovery process, but they're also very careful with their wording, in conjunction with...
Not discovered by.
Exactly. And as they clarify later, the final paper is entirely human-authored, aside from some excerpts in an appendix. They are framing the AI as a partner, a collaborator in discovery, not just a tool for execution or verification. This framing is a huge part of the paper's contribution.
It really sets the stage for a discussion about the nature of mathematical proof in the 21st century.
It does. It's a landmark statement.
That concludes the abstract. Everything covered.
Absolutely. We are now moving to Section 1, Introduction.
Okay, Section 1, Paragraph 1. Here they give a more formal definition of the flag variety. They read, 5NN plus 1 equals GLN plus 1 B borel dollars LN plus 1 equals GLN plus 1 divided by B.
And this quotient representation is key. We touched on this, but let's dive deeper.
Yeah.
GL1 plus $1 is the group of all invertible $1 plus $1 by an $1 plus $1 matrices. It represents all possible changes of basis for the underlying vector space, $O plus B. $$ is a Borel subgroup. Specifically, for Jalaro plus Delawan, it's the group of all invertible upper triangular matrices.
So why does dividing the whole group by the upper triangular ones give you the space of all flags?
Think about what a flag is. It's a sequence of nested subspaces. There's a standard flag, the one you get by just taking the spans of the standard basis vectors. What matrices will preserve that specific flag?
They can't mix up the basis vectors too much. An upper triangular matrix will map the first basis vector to a multiple of itself, the first two to a combination of the first two, and so on.
Exactly. The Borel subgroup Bora dollars is precisely the stabilizer of the standard flag. It's the set of all transformations that don't change that one specific flag.
I see. So the general theory of group actions says that if a group acts transitively on a space, meaning you can get from any point to any other point, then the space itself is isomorphic to the group divided by the stabilizer of a single point.
You've got it. Since any flag can be transformed into any other flag by some matrix in GLN plus 10, the action is transitive. So the space of all flags is just GLN plus 1B1. This isn't just a definition, it's a deep structural statement about the homogeneity of the flag variety.
And they connect this to the sequence of quotients, Kana plus 1 two-head right arrow and two-head right arrow, E11K to the N plus 1 surgex onto En, and so on, down to E1, where the dimension of ACO is the dollars.
Right, that's the geometric interpretation of a point in the quotient space. Each point corresponds to one specific way of constructing this tower of quotient spaces.
That covers the definition of the complete flag variety and its quotient representation. Have we missed any crucial structural points?
We've thoroughly unpacked it. The key is the homogeneous space structure. Let's move to the universal bundles.
Paragraph 2. They introduce the universal sequence over the flag variety itself. 1, 1, all 1, 1, FLN plus 1, what's 1, two-head right arrow, 1, 11, 11, plus two-head right arrow, 2, 11. Okay, so the notation, 1 plus 1 plus 1 FLN plus 1 dollar. The trivial vector bundle O to the N plus 1 over FLN plus 1 just represents the total vector space, so $1, but now thought of as a constant bundle over every single point of the flag variety.
So for each point in the flag variety, which is a specific flag, you just attach a copy of the whole space, $n plus 1L.
Right. And the magic of moduli spaces is that the very objects you are parameterizing, the flags, can be organized into vector bundles over the parameter space. So at each point in FLN plus L1, which corresponds to a flag, the fiber of the bundle ECA is precisely the t-dimensional quotient space from that flag's definition.
It's like the space is made of its own building blocks. This is what's meant by the universal property, right? It's the one bundle that contains all possible flags simultaneously. Yes, exactly. It's universal because any other family of flags you can construct can be obtained by pulling back this one universal sequence. This setup is crucial because, as we'll see, the degree of a map is defined by what it does to these universal bundles.
Okay, universal bundles defined. Proceeding to the definition of the map space itself.
Acknowledged. Let's define the space omega 2 beta plus $1 emperor precisely.
Paragraph 3. Here's the full definition, and they focus on a key technical condition. The base point constraint, which is written 5.1 $IFCAL equals ID do.
And that's pronounced F, evaluated at the base point 1 to 0 equals the identity flag. The point $1 is just a standard choice for a base point on the projective line. Math BBP20, you can think of it as the point at infinity.
And II is the standard flag we just talked about, the one stabilized by the Borel group. So every map we're considering has to send infinity on our sphere to this one specific standard flag in the target space. Why is that so important?
It's a normalization. It pins down the maps. Without it, you'd have an extra copy of the flag variety itself floating around because you can just, rotate your whole setup. By fixing one point, you remove that ambiguity. It makes the space much more well-behaved, and crucially, it simplifies how the vector bundles behave when you pull them back with the map $5.
So it's a technical choice, but one that makes the whole problem tractable.
It's absolutely fundamental. The geometry of the pullback bundles depends heavily on this basing condition.
Definition and base point constraint covered. Moving to the degree class betas itself.
Let's unpack how a meta is represented.
Paragraph 4. They state that the group of one cycles on the flag variety is isomorphic to a lattice. The isomorphism is $, FLN plus 1 called nath BZN. The tau group in dimension 1 of FLN plus 1 is isomorphic to Z to the N.
Right. So this is saying that the ways a curve can wrap inside the flag variety isn't just one number, like in simpler spaces. It's described by not all separate integers. It's an odd-dimensional notion of degree.
And they define these integers explicitly. They are the components of beta I, which are take AI dAI equals the degree of the pulled back vector bundle EI.
So this is where the universal bundles come back into play. You take your maps, the math BVP diddled run into the flag variety. You use that map to pull back each of the universal vector bundles, AII, onto math BVP.
And vector bundles over math BVP are simple. They just have a rank and a degree.
Exactly. So for each of the universal bundles, EDI, through $8, you get a number, its degree. That tuple of D dollars in DDI as DAGI is the degree class beta. It's the multidimensional signature of how your map is wrapping.
We now understand the structure of the degree beta. Let's analyze the critical condition imposed on beta.
Proceeding to the strict monotonicity condition.
Paragraph 5. This is a very short but absolutely essential paragraph. The degree beta D via TAI DII is called strictly monotonic if $0 BDIO is $0 DIIN psi.
So not just any collection of integers will do. They have to be positive and in a strictly decreasing order. Now, why? What is the rhetorical purpose, or rather the mathematical necessity of this condition?
It seems very specific.
It's the linchpin of the entire proof. Later on, when they build their tower of fibrations, the fibers will be defined in terms of certain vector bundles. The strict monotonicity condition, specifically the fact that DKK plus 1, 1, is precisely what guarantees that these vector bundles have what's called a positive splitting type.
Meaning all their constituent line bundles have positive degree.
Correct. And a vector bundle on math BBP 111 with a positive splitting type has very nice properties. In particular, its space of sections is well behaved, and its dimension is easy to compute. This positivity is the input needed for their key technical result, proposition 2.3, to hold. Without strict monotonicity, the class of the fibers would not be constant, and the entire proof strategy would collapse.
So this isn't an arbitrary choice. It's a carefully selected condition that enables the entire mechanical structure of the proof.
Precisely. It's the key that unlocks the whole thing.
The crucial constraint is now defined. Let's immediately dive into the main theorem itself, Theorem 1.1.
Let's do it. Theorem 1.1.
All right, reading the theorem statement. For a strictly monotonic beta, theta equals D1 L dots, DNOs, the class of the map space is given by, and here's the formula, omega 2 DN LNS DLN plus 1 DLN times AD frac n.
And we pronounce those terms as the class of omega squared sub DN dot 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 D1 of FLN plus 1 on the left,
right,
and the class of GLN times the affine space A to the D minus N squared over 2 on the right.
And they define that exponent DLR. It's DL$ sum K1n 2dk n of DL equals the summation from K equals 1 to n of 2dk.
Right, so DLR is just a simple sum related to the degrees. So what is this theorem really saying now that we have all the pieces? It's saying that this space, parameterized by rational functions, which can be, incredibly complex and have singularities, this space, when viewed in $40K$ is equivalent to a simple, well-understood Lie group times a featureless affine space.
It's a profound statement about hidden simplicity. But it's crucial to remember this is an equality of classes, not of the spaces themselves.
Yes, that's the whole point we'll see, illustrated by the counterexamples later. The actual geometric spaces can be wildly different, but their point counts, their motivic shadow, are identical.
We've fully parsed the statement of Theorem 1.1. Let's analyze the immediate consequence.
Let's look at the point counting consequence.
Paragraph 6. It's very direct. Theorem 1.1 gives an equality of point counts over finite fields. See Corollary 8.1.
And this is where the rubber meets the road. This is the highly testable numerical prediction that comes out of the abstract machinery. There's what's called a point count evaluation map that takes you from the Grothendieck ring, K$ arc, to the ring of integers math, or more generally, to a polynomial ring, math BBCQ.
And this is the map that sends our special variable dollar to the number of points in the field, $2.
Precisely. So you take the beautiful formula from Theorem 1.1, you replace every instance of the class GLN$ with the known polynomial for its number of points, and you replace every dollar with a dollar. The result is a concrete formula that predicts the number of rational maps of a given degree over any finite field.
And this is what originally drove the research and what they likely fed to the AI in the first place, a concrete counting problem.
Yes, that was the entry point. The abstract motivic result is far more powerful, but the point count is the verifiable core.
The connection to point counting is established. We move now to the motivation, the topological context.
Let's pivot to the topological motivation. This is in paragraphs 7 through 14.
The authors draw a parallel. They compare their algebraic space of maps, omega 2 beta, FLN plus $1 to its topological counterpart, which they call omega 2 beta top FLN plus $1.
Right. So if you're working over the complex numbers, the flag variety is also a topological space, a complex manifold. You can study continuous maps into it, not just algebraic ones.
And there's a known result here, a theorem by Boyer-Hurtubise-Mann-Milgram. They say that for very large degrees the beta, the algebraic space is a good approximation of the topological one.
It gets better and better as the degrees go to infinity. Specifically, it's a k-beta connected approximation, where data gets larger with beta-beta. This establishes a bridge between the two worlds.
And in the topological world, there's a known beautiful simplification. They mention the equivalence omega 2 top dan plus 1 and nn1.
Okay, let's break that down. First, the flag variety, day1 plus 1 by 2, is topologically equivalent to the space dou(n plus 1t, where dou(n plus 1dn is the unitary group and $2 is a maximal torus. For homotopy purposes, this is very similar to del(n plus 1 itself.
So studying maps into the flag variety is like studying maps into the unitary group. And the notation for the topological space of maps is omega 2 beta top FLM plus 1. Omega squared sub beta comma top of FLN plus 1 is a homotopy equivalent to omega squared top of UN plus 1.
Exactly. And the known result is this astonishing simplification in topology. The double loop space of the unitary group 1 plus 1 is rationally homotopy equivalent to the simpler group 1 plus 1. That's omega squared top of UN plus 1 is rationally homotopy equivalent to UN.
So just like our main theorem reduces 1 to log to log dollar, the topological version does the same. This suggests the algebraic result isn't coming out of nowhere. It's the algebraic shadow of a known topological phenomenon.
It provides strong motivation. The expectation would be that since GLM and ODE are out on the same rational cohomology, our main theorem is the perfect algebraic analog of this topological fact.
But then comes the big caveat. The crucial sentence. They state that for intermediate, strictly monotonic degrees, the algebraic space fails to have the rational homotopy type of Euclid.
This is the critical tension. The motivic class simplifies, always. The topology only simplifies in the limit. For any specific finite degree, the algebraic space is actually more topologically complex than its ultimate target when buying.
Which is exactly why the theorem has to be in k$var. The Grothendieck ring is the only place where this simplification holds universally for all strictly monotonic degrees. It sees a deeper, simpler structure that the full topology obscures.
Perfect stated.
The topological context, including the rational equivalence in the failure cases, is detailed. What is the most ambitious outcome suggested by the k$var result?
Conjecture 1.2 on cohomology.
Right. They put forward this optimistic conjecture 1.2, which reads omega 2 beta FLM plus 1 math BBQ Kong HUN.
So that's pronounced H star of omega squared sub beta of FLN plus 1 with coefficients in the rationals is isomorphic to H star of UN with coefficients in the rationals.
They're conjecturing that even if the spaces aren't the same from a homotopy perspective, their rational cohomology rings are identical. This is a much stronger claim than the MOTIVIC one.
It is. The MOTIVIC class matching is strong evidence because for smooth projective varieties, the cohomology is determined by the motive. But these map spaces are not smooth or projective, so it's a genuine conjecture. It says that the deep algebraic invariants of the map space are exactly those of the simpler unitary group.
It's a bold and beautiful prediction, directly inspired by their main theorem.
It's the next great open question that this paper poses.
Conjecture 1.2 is fully stated. We transition now to related work.
Proceeding to section 1.1, related work.
In paragraph 16, they situate their result. They acknowledge the foundational work of Segal and Kirwan on related spaces, and note that their work generalizes a previous result by Farb and Wolfson, which handled the simpler case of Grassmannians.
This is standard practice, of course, but it's important. They are showing that this isn't a bolt from the blue. It's building on a rich history of trying to understand the topology of algebraic map spaces, and their result for the full flag variety is a major generalization.
The background context is set. This leads us to the crucial discussion of AI collaboration.
Let's begin the breakdown of section 1.2.
Section 1.2, the role of AI. They get very specific here in paragraphs 17 through 21, naming the tools, Gemini, DeepThink, and an internal system called Foolproof.
And they describe their initial strategy, which they call scaffolding. The idea was to not ask the AI to solve the whole grand theorem at once. They started with the point counting version, corollary 8.1, and even then, only for small values of non-Dillon-Iyer.
So they were giving the AI concrete, verifiable numerical problems to solve. Find the formula for phi and this specific degree. Now find it for $2,300.
Exactly. And this leads to what is, for me, the most interesting sentence in this section, the initial failure. They state very clearly that the AI could not solve the general problem without human intervention.
This is so important. It tells us we're not at the stage of just handing off problems to a machine oracle. The process was interactive. It required a feedback loop.
It proves that a leap of abstraction was needed that the system at that point couldn't make on its own.
The initial setup the AI systems used and the failure of the first attempts are all noted. Now, the successful iterative loop.
We analyze the 4 steps of collaboration.
Paragraphs 22 through 25 detail this loop. Step 1. AI solved the special cases. It spat out the correct point-counting formulas for small dollar and beta dollar.
Then comes the human step, step 2. The human mathematicians looked at the pile of concrete formulas generated by the AI and searched for a pattern. And they found the crucial one.
They noticed that the formula seemed to be independent of the splitting type of the vector bundles involved.
This is the moment of genius. The AI sees numbers and polynomials. The human sees an underlying principle. The answer doesn't depend on the fine-grained geometry of the intermediate bundles. This insight is what became the core of the proof, the idea that the fibers in their tower had a constant motivic class.
So step 3. The humans took this abstract idea and used it to formulate new prompts for the AI, essentially hinting at the general strategy. Try to prove that the class is independent of the splitting type.
Right. They guided the AI's search toward the abstract principle they had discovered. And then, step 4. The reprompted AI was able to generate the complete proof for the point-counting corollary and then generalize that to the full motivic theorem.
It really was a partnership. The AI was a phenomenal pattern matcher and formal proof generator, but the human role was to make the key abstraction, to translate a list of results into a mathematical strategy.
That's the perfect summary. The human provided the meta-strategic insight.
The successful human AI strategy is fully described. How does the final paper relate to the AI's output?
Assessing AI originality.
Paragraphs 26 and 27. They note that the final human-written paper only bears a high-level resemblance to the AI output. But, and this is key, the proofs generated by the AI, especially from the specialized full-proof system, were very accomplished.
And their conclusion is a powerful one. They argue the AI's contribution involved a genuine combination of synthesis, retrieval, generalization, and innovation. This wasn't just looking things up, it was synthesizing known mathematical techniques in a novel combination to solve a new problem. They are making a strong claim for genuine, if guided, mathematical discovery by the AI.
Section 1.2 is entirely completed, concluding the methodological discussion.
We are moving to section 2, proof of the main result.
Okay, section 2.1, paragraphs 1 through 4. This is where they set up the main engine of the proof, the tower of fibrations.
Right. The strategy is decomposition. Instead of attacking the full space omega-2 FLN plus 1 at once, they break it down. They define partial flag varieties, 5LN plus 1K, which only parameterize the first table steps of the flag.
This creates a tower of spaces where each one maps to the next one down by just forgetting the last piece of information.
Exactly. You get a sequence of maps, a tower of fibrations. The map is omega-2 dk to omega-2 dk plus 1 omega k plus 1, omega-2 dk plus 1, omega squared sub dn dot 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 dk, FLN plus 1 comma to omega squared sub dn dot 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 dk plus 1 of FLN plus 1 comma k plus 1. The whole goal is to calculate the motivic class of the fiber of this map, P1K.
Because if the fiber class is constant, you can just multiply them all together to get the total class.
Precisely. It turns a single, impossibly hard problem into a sequence of nuller manageable, identical problems.
The tower structure is established. We define the key section notation.
Definition 2.1.
Here they introduce 4 different notations for spaces of sections of a vector bundle $5. The crucial one for the proof is NPF n sub p of f.
Right. This stands for the space of based, nowhere vanishing sections. Based means the section has to take a specific value at the base point, and nowhere vanishing means, well, it never hits 0. This is the space that will turn out to be isomorphic to the fiber of their tower.
Okay, definition 2.1 is clear. We proceed to the lemma that converts the fiber problem.
Lemma 2.2.
This is the key isomorphism. It reads d pi 1k f cong ak plus 1 ek dk plus 1.
The pronunciation is the fiber pi k inverse of f is isomorphic to n sub vk plus 1 of ek plus 1 twisted by the difference dk minus dk plus 1. So this is the heart of the geometric argument. Let's walk through the proof step by step.
So the fiber, p pi 1k, is the space of all possible ways to choose the next quotient space, ek dollars, given that you've already fixed the map $5 up to the level k plus step up.
Right. And choosing a quotient ek, 2 pi pi, is the same thing as choosing its kernel, which is a rank 1 subbundle inside ek plus $1.
Okay, so the fiber is the space of choices for the subbundle $2.
Yes, now here comes the deep dive on vector bundles on math BBP Fano. Grothendieck's theorem is a miracle. It says any vector bundle ek over mo splits into a direct sum of line bundles. This structure is incredibly rigid and predictable.
So our bundle $2, being rank 1, is just a line bundle, thorn-d for some degree dd. And we have an embedding of this line bundle into the bigger bundle ek plus 1.
Correct. And here's the beautiful algebraic trick. An embedding EP1D to EI is algebraically equivalent to a global section of the twisted bundle EDE, which is E times O math PP1 to G.
Ah, so you twist the target bundle by the inverse of the thing you're embedding.
Exactly. It turns the problem of finding a subobject into the problem of finding a section, which is often easier to analyze. And since the subbundle torlog can't be 0, the corresponding section must be nowhere vanishing. And the base point condition on the map translates to a basing condition on the section.
So the space of choices for $3 is precisely the space of based, nowhere vanishing sections of a twisted version of ETA plus 1. That's the lemma.
That's the lemma. It's a beautiful piece of classical algebraic geometry.
Lemma 2.2 is proven. We now calculate the motivic class of MPE in general.
Proposition 2.3.
This is the result born from the human analysis of the AI's output. The formula is NPE LDR plus 1. The class of NT of E equals L to the D minus R plus 1 times the quantity L to the R minus 1 minus 1.
And this holds under one condition, that the bundle dollar has a positive splitting type, meaning all its component degrees A or at least 1, or an equivalent condition that a certain cohomology group, 1AT2, vanishes.
And the proof. How do they show that the class only depends on the rank, Tor, and degree, not the individual days?
They use a clever stratification argument. They relate the class as all base sections to the classes of nowhere vanishing sections. The space of all sections is easy. It's just an affine space, so its class is a power of dollars.
And they find a recurrence relation.
Yes. The identity is essentially sigma E1, NP EK1. You can see that by twisting the bundle, you shift the degrees, but the rank stays the same. When you solve this simple relation, all the messy details about the individual splitting types just cancel out. You're left with a formula that only sees the total degree and the rank.
It's an algebraic confirmation of the pattern the AI's data suggested. The fine geometric structure is invisible to K dollars for...
Precisely. It's the technical core of the paper's main insight.
Proposition 2.3 is proved, establishing the constant class assumption. We apply this to the fiber.
Corollary 2.5.
The corollary just plugs in the details. The formula for the fiber class is P1K, F, LK plus 1DK, LK plus 1DK plus 1K.
And this is where we see why strict monotonicity was so important. The vector bundle in question from lemma 2.2 has its positivity guaranteed by the fact that DK plus $1 O. That condition ensures the positivity requirement for proposition 2.3 is met.
So the whole chain of logic holds.
It holds. And the fiber class is therefore independent of the specific map dollars you chose in the base. It's constant. The authors then just walk through the calculation of the rank, which is 2RK plus $, and the total degree dollars to verify the exponent in the formula.
The constant fiber class calculation is complete. We need the final theorem that makes the product possible.
Proposition 2.7.
First, definition 2.6. A fibration is motivically trivial if, even if the fibers aren't isomorphic, their motivic class is constant across all strata of the base.
Right. And Proposition 2.7 proves that their tower of fibrations is in fact motivically trivial. The proof of this is in section 2.3, and it's probably the most technically advanced part of the paper.
It relies on stratifying the base space.
Yes, by two things, the splitting type of the bundles and something called the base point depth. But the key insight, and this requires another deep dive, is about the structure groups involved. This is where we need to talk about special algebraic groups.
Okay, what makes an algebraic group special?
A group like GENUS, or the additive group math.AG, is special because any principal bundle with that group as its structure group is guaranteed to be Zariski locally trivial. This is a very powerful property. It means that locally, the bundle just looks like a direct product.
And the groups that show up in the stratification of their base space are built out of these special groups.
That's the crucial geometric fact. Because the stabilizers are special, they can show that over each stratum, their fibration is locally a product. And because we're in KL values of R, locally a product is good enough to say the whole thing behaves like a product. It's what allows them to multiply the class of the fiber by the class of the base.
So this deep property of algebraic groups is what provides the final glue to hold the entire tower argument together.
Absolutely. It's a very sophisticated piece of geometry.
The tower is proven to be motivically trivial. We can now finish the main theorem.
Section 2.2.
Here they just put it all together. They have the base case of the tower, which is just a point, so its class is 1. They have the constant class of every fiber. So the class of the total space is just the product of all the fiber classes.
They write out the product, omega 2dn, LKN, LK1n, LK1, L prod, LK1 double, where alpha is the sum of all those complicated exponents from the fiber calculations.
And they show that this exponent alpha telescopes and simplifies very nicely to alpha d binom n plus 1 nothing.
Right. And now they just need to match this with their target, GLN times A and E. They use the known formula for the class of the general linear group. It's GLN L binom K1, 2. The class of GLN equals L to the binomial coefficient n choose 2 times the product from k equals 1 to n of the quantity L to the k minus 1.
And look at that. The product term is identical.
It's a perfect match. So you can just factor out the class of GLN. What's left over must be the class of the affine space factor, which is just dollars in power.
So the final step is a simple subtraction of exponents. You take their total exponent alphas and subtract the exponent from GLN2. The result is del r by n plus 1, 2.
And a little binomial identity, d by n plus 1, 2 plus binom 2, n 2, 2, gives you the final result for the dimension of the affine space. $52, which is exactly what the theorem states. The proof is complete.
An absolute beautiful argument from a complex geometric problem to a tower to fibers to sections and finally to a simple algebraic cancellation.
It's a masterclass in this style of motivic calculation.
Theorem 1.1 is now proven. We finalize the discussion by looking at the negative examples that define the limits of this theorem.
Section 2.4.
These examples are so important because they show what you lose when you pass to $kk vars. Example 2.9 looks the simplest non-trivial case. 1 Mahler, mapping to math BP plane, with degree 2 height to 2. The space is omega 22.
Our theorem says its motivic class should match that of GL1 times ALOA. GBL1 is just the multiplicative group, math BP2, whose class is old Dulles. It's topologically a cylinder, or homotopy equivalent to a circle, $.
A circle has trivial higher homotopy groups. Its pay P2 is 0.
Right. But the map space omega 22 math BP1 is known to have a non-trivial second homotopy group. Pi22 is isomorphic to the integers, math BPN. It has a hole in a higher dimension that the circle doesn't.
Which means they cannot possibly have the same rational homotopy type. They are fundamentally different shapes.
And yet their motivic classes are the same. This is the perfect illustration of what the growth integer group ignores. It's blind to this kind of topological complexity.
Example 2.10 drives the point home even harder by looking at the fibers themselves. They look at a case for 1s and e2 and show that depending on which 0.5 you pick in the base, the fiber 1s S and F can be 2 completely different varieties.
In one case, depending on the splitting type of the bundle at 5 Aller, the fiber is isomorphic to math.AT, a simple topologically boring space.
But for a different dollar with a different splitting type, the fiber is isomorphic to the very space we just discussed, omega 22, which is topologically complex.
These two spaces are not isomorphic. They aren't even homotopy equivalent. And yet, our proof relied on the fact that they have the exact same motivic class. This confirms why the concept of a motivically trivial fibration was so essential. The geometry of the fibers changes, but their algebraic shadow does not.
The limits of the theorem in terms of rational homotopy and isomorphism class are established. We process the final appendices.
Proceeding to Appendix A.
Appendix A just briefly recaps the steps of the AI discovery that we already discussed. Appendix C contains excerpts of the AI's actual output from full proof, and the paper ends with references and author affiliations.
And with that, we have covered every single line of the document, from title to the final author email.
Okay, so let's just step back for our outro. This deep dive has really shown, I think, both the immense power and the specific limitations of using the motivic class.
It has. The authors, with this unprecedented human-AI collaboration, show that these wildly complicated geometric spaces of rational maps have a deep, hidden combinatorial simplicity. They all collapse down to the class of DOI times AI.
And the entire proof, the entire breakthrough, really hinged on that one core human insight that was sparked by the AI's data. The realization that the messy geometric details, like the splitting type, were completely irrelevant in K's dollar. That led to the constant fiber decomposition.
Yes, the AI provided the overwhelming numerical evidence, and the humans provided the crucial abstract leap, a true partnership.
But the tension we kept coming back to remains. The negative examples prove that you achieve this beautiful simplification at a cost. You become blind to essential topological features like homotopy groups. The ring just doesn't see them.
Which brings us to a final provocative thought for you to take away. We've seen that the growth in ELEK group loses critical information about the shape of a variety. The next frontier in this field might be to invent a new algebraic ring, a sort of homotopy-aware growth-endic ring, one that is still simple enough to allow for these powerful reductive techniques like the tower of vibrations, but somehow rich enough to not forget the topological information that K to bar reservoir throws away.
Could you even build such a thing?
That's the billion-dollar question.
Yes.
But here's the twist. Given that an AI system like Foolproof was so central to synthesizing the techniques in this paper, is it possible the discovery of that new, more powerful algebraic structure won't come from a human mind? Could an AI, building on the foundation of synthesis we see right here, be the one to make that next great abstract leap?
The fascinating and slightly unsettling thought to end on. Thank you for joining us on The Deep Dive. We'll be back soon with more insights from the cutting edge of research. Welcome back to The Deep Dive. Today, we're tackling one incredibly dense and I think beautiful paper. Our goal is to break it down until you, our learner, are the most informed person in the room.
And we are absolutely honoring the spirit of discovery today by engaging what we call the unabridged protocol.
Right.
This isn't a summary. We're going to process this source strictly, linearly, assuming we have all the time in the world to get to the deepest possible conceptual level.
That's the mission. Granular knowledge that goes way beyond just reading the abstract. And our subject is right at the bleeding edge of algebraic geometry and topology. We're talking about really complex spaces of maps.
The paper is titled, The MOTIVIC Class of the Space of Genus Zero Maps to the Flag Variety, by Jim BRYAN, Palacios ELEK, FREDDIE Manners, George Salafatinos, and RAVI VAKIL.
Okay, so let's start right there. The MOTIVIC class of the space of genus zero maps to the flag variety. This title alone tells us exactly what we're studying and how we're measuring it.
It really does. There are three core elements here that define the whole field of play. First, the method of measurement, the MOTIVIC class.
Okay.
This is a formal classification inside what's called the growth-endic group of varieties. It's a very robust invariant that measures things up to cut and paste equivalence. Think of it as measuring the fundamental composition, not the specific shape.
So it's a structural metric, not a purely geometric one. And the things being measured, genus zero maps?
Precisely. In algebraic geometry, genus zero means you're dealing with objects like the Riemann sphere, or algebraically the projective line, which we write as math baby P11P1. It's the simplest possible compact curve, which sets the stage for the simplest, non-trivial maps.
And their destination, the target space? The flag variety?
The flag variety, which they denote 5L plus 1 of LFL subscript n plus 1, is this amazing geometric space that it parameterizes nested sequences of subspaces inside a larger vector space. It's a very symmetric, very complex target that's just fundamental in a lot of areas.
Right. And just to confirm the contributors again, Jim BRYAN, Palacios ELEK, FREDDIE Manners, George Salafatinos, and RAVI VAKIL.
Okay, so I think we've thoroughly unpacked the title's implications there and, acknowledged the contributors. I think we've set the stage. We can proceed to the abstract.
Fantastic. Let's start with the first sentence of the abstract, which sets up the key players.
The source text reads, let 7FL plus 1 FLML subscript n plus 1 be the variety of complete flags in math BBA n plus 1a to the power n plus 1, and let omega squared beta of FLM plus 1, omega squared beta of FL subscript n plus 1 be the space of based maps $5 math BB1 to FLMP1 to FL subscript n plus 1 in the class beta F star of the class P1 equals beta.
Okay, let's go piece by piece. We have the flag variety final FL1 plus 1 plus 1 of L subscript n plus 1. And it's parameterizing flags in it's math baby n plus 1a to the power n plus 1, which is just a fine space.
Right. And the main object of study is this space, omega 2 beta, omega squared beta of FL subscript n plus 1. That notation, omega 2 omega squared, is a direct nod to algebraic topology. Maps from the two-sphere are called double loop spaces. Here, the domain is the algebraic version of that sphere, math BBP key 11.
Which means we need a quick foundational deep dive. Why the projective line math BBP Donna 11? Why is it so critical for these genus Theorem maps?
Well, as we said, it's the simplest complex curve. And it has this incredible property, thanks to the Grothendieck-Birkhoff theorem, that any vector bundle you put on it just splits apart into a direct sum of line bundles. All the complexity comes from these simple, well-understood components. It's what makes these calculations even possible.
Right, so you contain the complexity on the domain, and finally that condition, beta BDE star of the class of P1 equals beta, just filters the space. It says we're only looking at maps that represent a specific homology class, beta beta.
I think that establishes the core geometric setup clearly. We have the space and the maps. So let's proceed to the main assertion, which is really, I think, the shock value of the paper.
Okay, the second sentence, the result. We show that under a mild positivity condition on beta, the class of omega 2 beta, omega squared beta of FLL subscript n plus 1 in k dollars of var, k naught of var, the growth-ended group of varieties, is given by omega 2 beta FLN n plus 1. The class of omega squared beta of FL subscript n plus 1 equals the class of GL subscript n cross a to the power a.
Okay, we absolutely have to stop here. Mandatory deep dive on the Grothendieck group, k dollars of var, k naught of var, because if you don't get this, the entire theorem is just symbols.
Let's do it. So what exactly is k dollars var, k naught of var?
Imagine you have two really complicated shapes, these varieties, x and y. They might look nothing alike. But, and this is the key, if you can chop x to pieces, say x1 and x2, you can chop y into pieces, y1 and y2, and x1 is isomorphic to y1, and x2 is isomorphic to y2.
Then in the growth-ended group, they're considered the same.
Exactly. The class is the same. So you'd write sex x equals x1 plus x22. The class of x equals the class of x1 plus the class of x2. It's a way of measuring things based on this cut-and-paste equivalence. It's often called excision.
So why do we use it? Why not just stick with something more intuitive, like whether the shapes are identical?
Because demanding that varieties be isomorphic is just too strict. And demanding they be topologically equivalent can be way too hard to compute. So k dollars var, k naught of var gives us this coarser but incredibly useful invariant. If two varieties have the same MOTIVIC class, it guarantees other things, like their point counts over finite fields, will be identical.
That's the power. And the final result, omega 2 beta FLN plus 1 GLN times math beta. The class of omega squared beta of FL subscript n plus 1 equals the class of GL subscript n cross a to the power a it looks shockingly simple.
That simplicity is the surprise. The space of maps is notoriously complicated. We'll see later its topology is a real mess. But its fundamental composition, its motivic class, just collapses to the class of the general linear group, GLN, GL per day times the defined space, math BAA to the power A. And that affine space part is basically trivial.
So all the core complexity is somehow captured by GLN GLN subscript n, which is a very well understood object.
Yes. I think we've captured the essence of the equivalence and what the Grothendieck group is doing for us here. The paper now shifts to how they discovered this, which is a story in itself.
Right, the role of AI. The third and fourth sentences. The proof of this result was obtained in conjunction with Google Gemini and related tools. However, the treatment in this paper is entirely human-authored.
This is a really critical piece of context. They're drawing a very clear line. The final, rigorous presentation, the responsibility for it being correct, that rests with the human authors.
But the discovery was different. It was assisted by what they call very substantial input from Google Gemini, DeepThink, and a specialized system called Foolproof. So the AI wasn't just, checking their algebra. It was actively helping generate ideas.
Exactly. This split between AI-aided discovery and human-verified rigor is essential, and it's a theme we'll come back to when we get to section 1.2.
Okay. We've noted the AI's role and stressed the human authorship. The abstract is fully unpacked. I think we're ready to proceed to section 1, where the geometry gets defined in full detail.
Let's do it. We begin the introduction proper with the precise definition of the target space, the flag variety.
The first sentence reads, let fedelo n plus 1 in plus 1 b do e not L subscript m plus 1 equals GL subscript m plus 1 modulo b be the complete flag variety which parameterizes flags of quotients. Math BBD2 n plus 1, 2 head right arrow, 2 head right arrow, 2 head right arrow, EA01K to the power n plus 1 maps onto E subscript n, maps onto ... maps onto E subscript 1, where dim EK equals K, the dimension of E subscript K equals K.
So we have two definitions here, really, rolled into one. First, the group theoretic one. FLLN plus 1b dollar, FLFL subscript n plus 1 equals GL subscript n plus 1 modulo b. Here, GLN plus 1 GL subscript n plus 1 is the group of invertible matrices, and B is the Borel subgroup, think upper triangular matrices. It's a quotient space.
And second, what it actually parameterizes. It classifies these nested sequences of quotients EK, E subscript K. And a complete flag means you get one for every dimension, from T tall and all the way up to no dull.
Yes, so that's the setup. We've covered the technical definition of the variety. Now we need the universal sequence that lives on top of it.
Okay, sentence 2. There is a universal sequence of vector bundle quotients on phi alpha n plus $1 and 2 heterate n plus 1 FLN plus 1 2 heterate dollar 2 heterate r and 2 heterate r or and 2 heterate hours 2 heterate r 1 1. The trivial vector bundle O direct sum n plus 1 over FL subscript n plus 1, which equals E subscript n plus 1, maps onto E subscript n, maps onto ... maps onto E subscript 1.
This is universal because it just exists naturally over the flag variety. If you pick a point on the flag variety, which is a specific flag, and you look at the fiber of the bundle aka E subscript k over that point, you get exactly the k-dimensional quotient space for that flag.
So it's the structure we're mapping from. That sets up the target nicely. Now we can finally define the space of maps. Omega 2 beta, omega squared beta, precisely.
Right. The next paragraph gives the formal definition. Let omega 2 beta, FLN plus 1, omega squared beta of FL subscript n plus 1 be the space of genus 0 base maps in the class. Omega 2 beta, FLN plus 1, F math 1 plus 1, F1 plus 1. The set of F colon P1 to FL subscript n plus 1, such that F star of the class of P1 equals beta, and F of the base point 1 colon 0 equals the class of the identity.
Okay, so two big constraints here. First, the homology constraint, F beta FL star of the class of P1 equals beta.
Right, the map has to represent the class beta.
And second, the base point constraint, FUF $1 is IDDF of the base point 1 colon 0 equals the class of the identity. We're pinning down 1 point on the sphere to go to the standard flag.
Exactly. And they specify that beta in A1 FLN plus 1 beta is an element of the A1 Chow group of FL subscript n plus 1. That just means beta lives in the Chow group of 1 cycles, which is the algebraic version of the second homology group. It all fits together.
Okay, we've fully established the conditions defining our space. Let's interpret beta numerically.
Next sentence does just that. There's an isomorphism. A dollars, FLN plus 1. Simic math BBC. A1 Chow group of FL subscript n plus 1 is isomorphic to Z to the power n, such that the not triple associated to beta is given by D dollars, DN, comma, DIDI equals the degree of F star of EI.
So this simplifies everything. The abstract class of a beta is just a list of 19 integers, the das B subscript i's. And you get them by pulling back those universal bundles, the I subscript i's, to our simple domain math BVP 1 on, just calculating their degree.
Yes, this numerical translation is what makes the whole thing tractable.
All right, so we understand that the class is just this tuple of numbers. Now for that mild positivity condition from the abstract.
Here it is. We say that dbon, dntn, dnn, dn, 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 beta equals d1, comma, comma, dnn is strictly monotonic. If $0 dn, dn1, dn1 is less than dn, which is less than dn minus 1, which is less than ... which is less than d1.
It's a simple condition, but it seems really important. All the degrees have to be positive, and they have to be strictly decreasing.
Absolutely crucial. That strict inequality, dk plus 1 dk, is greater than dk plus 1 is non-negotiable. If you let them be equal, the geometry can get degenerate, and the whole proof strategy they use later, it just breaks.
Okay, that defines the strictly monotonic condition. We have all our geometric definitions in place.
We do, which means we can now state the main result, Theorem 1.1, with all the precise notation.
Theorem 1.1. Suppose beta d1 dn, beta equals d1, comma, comma, dn is strictly monotonic. Then we have the following equality in k dollars, k naught of var over k, the growth end group of varieties over math bbn d1, fln times math bbn, vatal n plus 1. The class of omega squared dn ... d1 of FL subscript n plus 1 equals the class of GL subscript n cross a to the power d minus n squared divided by 2.
And they define d, where d some k1 into d dk equals the summation from k equals 1 n of 2 dk. So d is just 2 times the sum of all the individual degrees.
The insight here is just spectacular. The final class doesn't depend on the specific values of the DL of is and D subscript i's, only on their total sum D, as long as they satisfy that monotonic condition.
Yeah.
Saying this space is structurally way simpler than its geometry implies.
Exactly. And that exponent, DL n 2d22 nan minus n squared divided by 2, that just tells you the dimension of that trivial affine space factor.
So we've deconstructed the main theorem. What does this deep algebraic result mean for something more concrete, like counting things?
Well, the paper notes. In particular, Theorem 1.1 gives an equality of point counts over finite fields.
Which is what we talked about earlier. If your base field math BBK is a finite field, math BBFQF subscript Q, then the number of points in our complicated map space has to be exactly the same as the number of points in the much simpler space, GLN times math BBBL subscript N cross A to the power A.
And that point counting problem was the initial target for the AI systems. It was a concrete numerical result they could aim for. We'll come back to that.
Okay, we've established the theorem and its consequences. I think we're ready to shift to the motivating topological context, which really highlights why this result is so important.
It does. The motivation starts by defining the topological version of our algebraic map space.
Source text, our original interest, is as an algebraic counterpart to the double loop space in topology. Omega 2 beta top is S2 to FLN plus 1, omega squared beta comma top of FL subscript N plus 1, the set of F colon S2 to FL subscript N plus 1.
So we're contrasting our algebraic maps, which are rational functions, with a topological space of all continuous maps from the two-sphere, CS2ES2. The omega 2 omega squared notation, again, tells you this is a double loop space in topology. The class beta beta now lives in T Mako Ln plus 1 H2 ES of she of FL subscript N plus 1, the second homology group.
And the two spaces are related. The paper says it's a natural inclusion, and a theorem by Boyer, Hurtubise, Mann, and Milgram says this inclusion is K of beta connected, where K of beta gets bigger as beta beta gets bigger.
This is a deep result. It means the algebraic space is a very good approximation of the topological one, and the approximation gets better and better for maps of higher and higher degree.
So it's good approximation, but not perfect. Now, what do we know about the topological side? The paper says there's a homotopy equivalence. Omega 2 comma on top of omega 2 top omega squared beta comma top of FL subscript N plus 1 is homotopy equivalent to omega squared top of U of N plus 1.
Right. The double loop space of the flag variety is equivalent to the double loop space of the unitary group, 1 UN plus $1 of N plus 1. This connects our problem to a cornerstone of modern topology.
And simplifies even further. The rational homotopy type of that space is known. Omega QN plus 1 omega squared top of U of N plus 1 is rationally homotopy equivalent to U of N.
Rationally homotopy equivalent. It means the topology matches if you ignore torsion. So this gives us our benchmark. The ideal goal is for our algebraic space to behave like the unitary group U1 of N.
Which sets up the central question of the whole paper. Question: how does the rational homotopy type of omega 2 beta, FL omega squared beta of FL subscript N plus 1 compare to the rational homotopy type of UN?
And we know it works in some cases. For the minimal case where beta in the 1 beta equals n comma n minus 1 comma dot 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 comma 1, there's actually an isomorphism of varieties. Omega 2n tan 1 tans math BBCN ON plus 1 FLN plus 1 simic GLN times math BBCN omega squared n comma n minus 1 dot 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 comma 1 of FL subscript n plus 1 is isomorphic to GL subscript n cross C to the power n, and that space does have the homotopy type of UN of n.
So in the simplest case, the expected topological result holds perfectly.
But, and this is why the paper is necessary, it doesn't always work. The paper states that for some finite non-minimal degrees, the space omega 2 beta, FLN plus 1 omega squared beta of FL subscript n plus 1 does not have the homotopy type of UNLN, not even rationally.
Wait, so for very small degrees it works, and for very large degrees it gets closer and closer, but in the middle, it fails. Why?
That's the crucial observation. The topology is too brittle. For some of those in-between degrees, the complexity of the algebraic definition creates non-trivial homotopy groups that just shouldn't be there if it were equivalent to Dröth-Venne. This is precisely why they had to move to the Grothendieck group. The MOTIVIC class is a more robust invariant. Theorem 1.1 succeeds where rational homotopy fails.
That completely reframes the main result. The MOTIVIC class is what's stable. The paper says their result implies that the weight polynomial of their space is the same as the weight polynomial for a variety that does have the homotopy type of Rubel of N.
Right. The equality in k-dollars of R, Connaught of R, means they have the same point counts, the same Betti numbers. It suggests a very deep common structure, even if the homotopy isn't quite right.
Which leads to this very optimistic conjecture, conjecture 1.2, that the rational cohomology rings are actually isomorphic. Omega 2 beta H star of omega squared beta of FL subscript N plus 1 over Q is isomorphic to H star of U of N over Q.
A much stronger statement. And Theorem 1.1 is the strongest evidence we have for it so far.
Okay, that completes the motivation. We understand the goal, the success of the MOTIVIC class, and the limits of the topological methods.
We can now move to section 1.1 on the related work. The paper credits the foundational work of people like Segal and Kirwan. but highlights that their proof methods generalize arguments from Farb and Wolfson, who worked on the simpler case of the Grassmannian.
That traces the lineage. Are we ready for the big pivot, section 1.2 on the AI collaboration?
Let's dive in. This is the narrative core. The paper starts by emphasizing that the text itself was written from scratch by the authors. But the proofs were discovered with very substantial input from Google Gemini, DeepThink, and an internal tool called Foolproof.
This confirms the landscape, human responsibility for correctness, AI as a catalyst for discovery.
And the collaboration didn't start with the final theorem. It started with the point counting problem, corollary 8.1. They used traditional tools like Macaulay 2 to get numerical evidence to get a solid conjecture to aim for.
And then came the scaffolding. They didn't just ask the AI for the answer. They framed the question as a series of sub-problems of increasing difficulty, even feeding the AI its own previous successful answers as context for the next step.
It's a very sophisticated way of prompting. But the key insight still required a human in the loop. The paper says none of the systems could prove the general result from that initial scaffolding alone. The breakthrough came from an iterative human-AI interaction.
And the sequence is fascinating. First, the AI solves the simple special cases.
Right.
Second, the humans analyze the AI's proofs and isolate the key intermediate step, the thing that could be generalized.
This is the crucial moment. The humans weren't writing the proof. They were debugging the AI's logic to find the missing conceptual piece. They realized the key calculation didn't depend on a variable the AI thought was important. That became proposition 2.3.
Third, they reprompted the AI with hints about this new strategy. Fourth, with that hint, the AI could generate the full proof for the point counting problem.
So the human provides the strategic insight, and the AI executes the rigorous proof based on that new framework.
And finally, they just asked the AI to extend that same argument to prove the full MOTIVIC result, Theorem 1.1. It's a phenomenal story of synergy.
And they address originality, saying the AI's output appears to be a genuine combination of synthesis, retrieval, generalization, and innovation. It wasn't just copying something from its training data.
So, a genuine discovery. Then section 1.3 is the acknowledgments, thanking Google DeepMind and the Blue Shift team. We've documented the full context. We're now ready for the technical heart. Section 2, the proof itself.
Right. The proof strategy is to decompose this complicated space into a sequence of simpler pieces. This is the tower of vibrations.
They start by defining partial flags, $5 n plus 1 k, laterella L subscript n plus 1 comma k. This is the space of flags that only go down to dimension k, not all the way to 1.
Exactly. And they create the tower with projection maps.
Yeah.
You have a map from 5L n plus 1k, L of L subscript n plus 1 comma k to 5L n plus 1k plus 1k plus 1 comma k plus 1k, just by forgetting the kthos space in the sequence.
The full flag space is at the bottom, $1, and at the top, you line plus another, you just have a single point.
Right. And there's a corresponding projection map for the spaces of maps, which they call PIC-PK. It just gets the k quotient bundle. The entire proof depends on calculating the MOTIVIC class of the fiber of this map.
So what's in that fiber? It's the space of all possible choices for that k quotient, given that all the bigger ones are already fixed.
Exactly. But to analyze it, we need a technical definition. Definition 2.1 introduces the space of based, nowhere vanishing sections, NPF, NP of F.
So this space, NP of F, NP of F, contains sections of a vector bundle F that are never zero and also satisfy a specific condition at a base point P.
Correct. And lemma 2.2 is what translates the geometric problem of choosing that k quotient into this abstract problem about sections.
Okay, so lemma 2.2 states that the fiber is isomorphic to one of these section spaces. EK dk plus 1 dk2. The fiber peak inverse of Strev is isomorphic to n subscript vk plus 1 of e subscript k plus 1 twisted by dk minus dk plus 1.
The logic is beautiful. Choosing the next quotient in the flag is the same as choosing its kernel. The kernel is a line bundle of negative degree because of the monotonicity condition.
The negative degree is key.
It is. Then they use a standard trick. An embedding of a line bundle of degree, say -5, is the same as an embedding of the trivial line bundle into your original bundle twisted by +5.
And an embedding of the trivial line bundle is just a nowhere vanishing section.
Exactly. So this complex geometric choice collapses into finding a simple, newer vanishing section of a twisted vector bundle. A brilliant reduction.
That translation is complete. Now we need to calculate the class of that section space.
That's the job of the calculation engine. Proposition 2.3. This is the master formula. It gives the class of NPE as NPE LER plus 1, The class in NPEE equals L to the power D minus R plus 1 times the quantity L to the power R minus 1 under a positivity condition.
And the most important part of this proposition is a single phrase. In particular, the class is independent of the splitting type of E.
That's it. That's the key intermediate statement that the humans extracted from the AI's output. The AI's special cases all have this property, and the humans realized it must be true in general. That insight is what unlocked the entire proof.
So this proposition holds regardless of the specific internal structure of the bundle E, as long as its components have positive degree.
Right, and the proof relies on stratifying the space of all sections by the degree of their common factor. This leads to an equation in the growth-ending group.
And the final trick is a telescoping sum. By applying that equation to the bundle E and the bundle E twisted by -1 and then subtracting, almost everything cancels out, leaving just the term they want.
It's an elegant piece of algebra that isolates NPE, the class of NPEV, and gives the final, simple formula. The computational core of the whole paper is right there.
That derivation is complete, and the uniformity of that result is incredible.
That uniformity is immediately applied in Corollary 2.5. It says the class of the fiber, the class of peak inverse of F, is constant. It's independent of the point phi of E you pick in the base space.
Which means we can just multiply the classes at each step of the tower?
Almost. There's a geometric hurdle. The paper points out that this map, PKE, is not a standard well-behaved fibration. The fibers aren't even necessarily isomorphic to each other.
This forces them to introduce a weaker notion, a motivically trivial fibration. The geometry can be messy, requiring a stratification, but the class of the fiber has to be constant across all the strata.
Exactly. And if that condition holds, the multiplication property still works in the growth-endiate group. So Proposition 2.7 states that their map is a motivically trivial fibration. They defer the proof of the stratification, but will accept it for now to finish the main calculation.
Okay, so section 2.2 puts it all together. The total class is just the product of all the fiber classes from k equals 1 to n.
Right. And that product splits into two parts, a power of L, which is the alpha dollars to the power alpha, and then this product of terms like log k1 and dollars to the power k minus 1.
And the genius part is the collapse of that exponent, alpha alpha. It's a big, ugly sum, but it's a telescoping sum, and it simplifies beautifully to alpha d frac nn plus 1 to val equals d minus n times n plus 1 divided by 2.
This is the moment that confirms the final class only depends on the total degree d. Now, they use the known MOTIVIC class of the general linear group, GLN L binom K1N L K1. The class of GL subscript n equals L to the power n. Choose 2 times the product from k equals 1 to n of L to the power k minus 1.
And they substitute that back in. The
Yeah.
product term is replaced by GLN dollars, the class of GL subscript n divided by a power of L.
Right. And when you do the algebra with the exponents, you find the total class is a power of L times the class of GLN to lay L subscript n.
Now we have to stick to the exact text. After the algebra, the paper concludes that the final formula is omega 2 dn SME AMOB ED1 FLN plus 1 LDNTM 22 GLN JO, the class of omega squared dn dot 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 d1 of p1 comma FL subscript n plus 1 equals L to the power d minus n squared divided by 2 times the class of GL subscript n as required.
And that completes the main calculation, assuming that stratification exists. So now we have to go back and prove it.
Right, section 2.3. Proving the fibration is motivically trivial, we need to stratify the base space.
The stratification has 2 parts. First, you partition based on the isomorphism type of the vector bundle, ek plus 1, e subscript k plus 1. This is standard, using the Birkhoff growth-endic theorem.
But second, and this is more subtle, you have to partition based on the depth of the fixed base point within the filtration created by that splitting.
Right, the depth tells you which components of the bundle the base point aligns with. So a single stratum is defined by fixing the splitting type, $3 in the depth.
And the proof that this works relies on the theory of special algebraic groups. What's a special group?
A special group G is one where all principal G bundles are automatically Zariski, locally trivial. It's a huge shortcut. If your structure group is special, you don't have to worry about local triviality. And the key examples are the general linear group, GL null of lethal GL of John L subscript M, and the additive group, JL jaw A.
And you can build more complex special groups from these.
Yes, and that's what they do. They show that the automorphism group of the bundle, automorphism group of ML-lore, is special. And more importantly, the subgroup that stabilizes a vector of a given depth, which they call GL-A, GL subscript R, L, is also special.
This sets up the final step, lemma 2.8. It says the map restricted to one of these strata is Zariski locally trivial.
The proof is to construct a principal GL bundle G subscript R, comma L bundle over the stratum. Because ELDR G subscript R, comma L is special, this bundle is locally trivial that gives you local sections. And those local sections are exactly what you need to build a local trivialization for the original map PKK.
And since that works over every single stratum and the fiber class is constant, proposition 2.7 is proven. The whole argument holds. We have fully proven theorem 1.1.
We have. Now we can look at the negative examples, which show why you can't push this result any further.
Right, section 2.4. Example 2.9 shows why the rational homotopy conjecture fails. They look at the simplest case. 1 nuller, degree 2, 2.
Here, the target space here, $of 1 is just a circle, which has a trivial second homotopy group, part T per P2.
But they show that the algebraic map space, omega squared 2 of P1, has a second homotopy group that is math BZ, the integers. It's not 0.
So the algebraic space has a hole that the topological target doesn't. They can't be rationally homotopy equivalent. And yet, theorem 1.1 still holds for this case. It shows how robust the MOTIVIC class is.
And example 2.10 shows why the fibration itself isn't geometrically trivial. They show that for different splitting types in the base, you get fibers that are not even isomorphic as varieties.
In one case, the fiber is a simple affine variety. In another, it's that complicated space from the previous example with the non-trivial topology.
So the geometry of the fiber depends on where you are in the base. But the MOTIVIC class of the fiber is always the same.
That's the definitive statement. The MOTIVIC class is the right invariant. It captures the stable structure that survives where isomorphism and homotopy fail.
Okay, we've analyzed everything. Now to the appendices, which detail the AI collaboration.
Appendix A states the original target was the point-counting corollary. It lays out the sequence. The AI solved special cases first.
Then the crucial step. The humans analyzed the AI solutions and noticed that a key calculation was independent of the splitting type.
That was the conceptual leap. The humans generalized that observation, conjectured proposition 2.3, and fed that back to the AI as a hint.
And with that hint, the AI could complete the general proof for the counting problem and then extend it to the full MOTIVIC theorem.
It's a perfect example of human strategic insight combined with AI's capacity for rigorous, large-scale execution.
And then, as a final test, they asked the AI if the result held for homotopy equivalence, and the AI successfully generated the counterexample we just discussed.
Which is incredible. It shows the AI can establish not just the proof, but the boundaries of the proof.
Appendices B and C just provide the source code, as it were, the prompts, and the sample of the highly rigorous AI output. We've seen the full story now.
This concludes the entire document, down to the references and the author addresses. The unabridged protocol is complete.
So what does this all mean for you, the learner? We started with this incredibly complicated space of maps. We found out its topology is erratic. It fails to match what we'd expect.
But the core finding, theorem 1.1, shows that its algebraic structure, its MOTIVIC class, is remarkably stable. It just collapses to the class of the general linear group times some empty space. From a compositional cut and paste perspective, the space is simple and uniform.
The relevance here is seeing the power of the MOTIVIC class as a stabilizing invariant. It's about knowing which mathematical lens to use when things get overwhelmingly complex.
But the really interesting part brings us back to that collaboration. Remember, the humans were essential, not for doing the millions of algebraic steps, but for isolating one single conceptual generalization from the AI's output.
Right.
The AI systems were necessary to execute the incredibly complex iterative proof once they had that key.
Which raises a profound question about the future of this kind of work.
It does. Given that these AI systems can synthesize and execute these massive generalized proofs once they're given a strategic conceptual framework, will the role of the human mathematician shift permanently? Will it become less about generating the proof and more about finding those key intermediate statements that guide an AI toward discovery?
The human as the strategic general and the AI as the flawless tactical executor. That is a profound thought to mull over.
Thank you for joining us on this incredible detailed deep dive.
We'll see you next time.